A quiz is going to be submitted on Canvas, and let's see. I guess we'll have my Canvas. So if we go to Canvas, if you go to the dashboard here, we can take a look. And you make sure we're on the right class, which is going to be Chem 4 1058. This will already have your fall classes, I think, populated in here. And then we'll go to quizzes here. There should only be one quiz here. Let me see, right here. Let me see if I could show you a different view. So it should look like this. This is a preview of the published version of the quiz. So this has been published. Then we'll just choose the file. And so I'm going to go here. I don't know why I didn't populate that. One unanswered question. Try a different file. A PDF file should work. Did anybody else have trouble with this, submitting the file upload? Marquise, you were able to do it? Hazra, no. Hazra, able to submit. Able to. Let me try a different file type. Okay. Well, let me sort it. It sounds like there are some people who are able to get it uploaded. Let me just take a look here. Oh yeah. So once you get it uploaded, then I can click it here. So I guess let's see how many people were able to upload it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. So if you're having problems, I'm having problems. I'm not sure why. Unless can somebody see what I was doing? If they're more familiar with it.
Good morning. I
wasn't able to. So I'll play around with it during the break.
Is there a limit to the ATMs outside?
If you weren't, don't worry about it. If you weren't able to upload it, eventually we'll get it figured out.
Okay.
Worst case scenario is if there's some deadline or something, just email it to me as an attachment. That'll work either through Canvas or my Gmail. Okay, were there any other questions?
Mm-hmm.
No. All right. Let's go back to the PowerPoint here. And look at this one. So going back, what are laws? I mean, where do laws come from? Like this law, for example, the law of conservation of mass. Typically, you know, yesterday I talked about two ways that one can derive or formulate laws. What were the two ways? These are the types of things that you think about. It depends on how much time you think about. You know, like if you have a lot of time, then you can ponder all different kinds of questions or think about things in different ways. If you don't have much time, then you're just trying to desperately like memorize certain things. But having the luxury of time is nice. So what you do is you're reviewing this stuff. This is why I reviewed this stuff every day, because when you review the stuff every day, it gives you time to think about things and then to actually picture things in different ways or see things in different ways. And I thought that was very helpful. So, you know, like yesterday is the first day. So yesterday would have been my first run through the notes. And then you run through, like today, I'd run through the notes from the very first day up to the present. And so it gives you time. So like, for example, you know, you might have noticed this. There are two ways that laws were derived. Catch it? What were the two ways that somebody can come up with laws? You can come off mute too. Again, just hold the space bar if you want to talk.
Count that.
Or, you know, just give me one way. It's fine. Where did laws
46.
come from?
Something like that.
1, 2,
48.
3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
So, you know, these types of things, this is good because it's good to, like I said, go back through your notes, and then eventually you'll have these things like memorized by the time you get to the final exam. Everything, the stuff from the beginning of class, you've seen it so many times, it's like burned into your mind.
44.
And so it's very important because it, okay.
Yeah.
Oh, you know what? My speaker is not working. Sorry. Let me see. Can you guys hear me? Okay, let me do this.
Well.
All right. Actually, I can't hear anything.
We can hear you.
Let me just test my audio for a second. Okay, sorry. You know what? My speaker was muted. I couldn't hear anything. So if you were talking, I missed everything because I was on, it's completely muted. Okay, so I don't know if anybody said any verbal comments because sorry, I had my speaker muted and so I couldn't hear anything at all. But I was asking earlier, you know, well, let me just continue on with what I was talking about. I was talking about, you know, this review. When you have the luxury of time to review things, then you can see things in different ways, and you can understand them in different ways. And so it's not something that, like, if you're cramming right before the test, then it's hard to see, you know, new relationships, or it's hard to see connections, you know, between things. Like one of the most common complaints from students on exams is that, oh, that particular question or this question or that question, you know, was nothing like the homework, or, you know, the professor never talked about that. That might be the case, but most times that isn't the case, and most times it's just they couldn't make the connection. You know, it was connected, but they just didn't understand the material well enough to make the connection. And so how do you get to understand the material well enough? You first, you just master the stuff. And so, like, Crystal, you're asking about the study guide. Yes, you're making your own study guide. What I'm telling you is that your study guide is the notes. If you have a complete set of notes that you review daily, by the time you get to the final, you've memorized. Let's say you have 90% of the information in your notes. By the time you get to the final, you're already guaranteed an A. Because, well, for most classes, you're guaranteed an A because, you know, 90% of the material is regurgitation. And then you can get that extra 10% because you have that base material so well mastered that you can do the advanced problems, the ones that people don't see the connections. A lot of people don't see these connections because they haven't given their, I did some, when I transferred to UCLA, because when I was at Santa Barbara City College, I was on the dean's list pretty regularly. It wasn't, but when I get to UCLA, everything changed, you know. All of a sudden, well, first I went to orientation. At orientation, they said, oh, your GPA is going to drop 1. And then I was pretty determined not to let my GPA drop 1. And so I worked really hard. I mean, my first quarter there, all I did was study and work. I had a job, but I devoted all my free time to studying because I didn't want my GPA to drop 1 whole GPA unit. And so, but it did. I was like, all of a sudden, like, it was also a transition from semesters to quarters. You have to be way more on top of it in the quarter system than semester system. I mean, semesters you can catch up, you know, later. But quarters, there's no time to catch up. You just have to stay on top of it all the time. So that was an adjustment, but I was trying to stay on top of everything all the time. And so I had to retweak the way I studied. So I started reading about studying and other types of things. But you do need time. You know, you need time to build these the neural network in your brain in order to make these types of connections. And in order to do that, you need time. You know, I remember one instance when I was at UCLA. I was taking a final, and there's one problem. It was a pretty challenging problem, and I was thinking about it. I had a lot of time because the other problems I had down, you know, with quick recall, and that gives you a lot of time to think about the challenge problem. But unfortunately, I couldn't figure it out. But I thought I was close. It was like something like on the tip of your tongue type thing, where you're very close to solving it. And so, well, that was only one problem, and so it wasn't that bad. And so I was right after the final exam, I went to Ralph's. You know, I just walked to Ralph's, and then I was standing in the checkout line at Ralph's, and then all of a sudden it hit me. You know, oh yeah, that's how you solve that problem. And so I wasn't even thinking about the problem, but I guess your subconscious thinks about that, and then all of a sudden the answer just comes. And so if I only had a little bit more time, if I only had like 20 more minutes, I would have had it. But it takes time to build those connections. So what you want to do is you want to get a start right away. And so when you're working on these types of things, you want to get the basic material down. It's not just memorization, you know, it's building that base in your brain so that you can make these connections. So one of the connections that you can make is, you know, or how or what were the 2 ways that I talked about laws being derived yesterday. Okay, just 1 second. Think about that, and go. Let me know. So these going on here, sorry about the interruption there, but going on here, you know, these are the types of things that, okay, after you see it, you read through your notes and then you make these connections. Oh, you know, I see the law and how are laws typically derived. And then I talked about one law that was derived in a different way. And so what you want to do is on the by the final exam, you want this stuff like automatic recall. That way you can work on the challenge problems, because this is just kind of what we call like just recall material. You know, you heard it before, you're just trying to recall it or remember it, and that's it. And it's easier to remember things, you know, the more times you see it. You know, it's like driving. Or riding, you know, a familiar path. And, you know, sometimes you don't even think, it's just automatic, because, and that type of stuff is very fast. It's automatic. You know, oh, you got to turn right here, you got to turn left there, you know, it just comes automatically. And that's how you want the information, at least this basic information down. That way, that gives you the maximum amount of time to, on exams, to work on the hard problems there. Though there are going to be problems that are going to be, fairly challenging. Like I said, about 10%. Most of the classes I had, about 10% of the test, but 90% was just recall. And if you can recall it fast, then you can. And unlike like here at El Camino, I have a different philosophy. I never liked timed exams. You know, at UCLA, all exams were timed. You know, and not only that, all the exams were longer than what you could finish. You know, they had more questions so that nobody, you know, should get 100%. You know, everybody should be below 100%. That way they can spread everybody out, because if everybody, if their whole cluster of people at 100%, then how do you know, how far up the scale actually goes? So they always put something very hard on the tests to try to keep it out like that. But anyway, getting back to this, yeah, through the scientific method, but what more specifically through the scientific method? So patterns and trends, right? What we wanted to see is we want to see consistent patterns and trends. If these patterns and trends can be defined mathematically, then we can come up with empirical laws. Most laws are derived empirically. And what does empirical mean, or empirically mean? Most laws are empirical in nature. Yeah, from observations. So they're just derived from observations. You see a pattern, you know, like an apple falling from a tree. You see a pattern, apple falling from a tree, you know, how long does it take? You know, how fast is it going? And then you can come up with some, maybe some mathematical equations to define that pattern. Like, and those mathematical equations can turn into laws if they're consistent. So, and they do, like apple falling from the tree is the classic story of Newton. And he derived Newton's laws. Newton's laws are empirical, you know, just from measurements of how fast things fall and how long it takes, and that type of stuff. And then we can get Newton's laws of physics that way, and Newtonian physics. The same thing, you know, here. What was the other way that the law was determined? Well, experimentation and observation are the same thing, basically. When I say observation, we're doing an experiment. That is, we want to do quantitative observations. And when you do quantitative observations, then you got to set up the equipment. You got to make sure you're taking precise and accurate measurements and this type of stuff. So observation and experimentation are synonymous. Oops. Okay, my battery's gone. One second here. There we go. Less consistent patterns with exceptions, Adriana. No, less consistent patterns with exceptions, we don't call laws. We give it another name. If you have a less consistent pattern with exceptions, we call those what? No, theory is the ultimate. We call those rules, Kazar. That's correct. So Kazar has it right. A theory, you know, ultimately what we want is theory, because with a theory, you get two things, you know, with a theory. What two things do you get with a theory? See, this should be very fast recall. Maybe it's not so fast because you might have just read it once, or, you know, some people don't even read their notes. You know, some people wait until the night before the test and then try to cram it in, but it's impossible. You know, impossible to get, you know, a high score on the exam. I guess they just want to struggle and hopefully pass the class. But the cramming is not effective at all. Sometimes you get lucky, you know. I don't say don't cram, because, you know, you always, if you got time, go up, yes, cram, but you want to. It's like, yeah, you got to watch out for the correction. It's accepted fundamental description, yeah, description. So it describes the phenomena. So a theory can describe, you know, your observations, or your theory describes how nature operates, basically. And it should be able to do one more thing. What should it be able to do? A hypothesis and a theory are essentially the same kind of thing, except the hypothesis is your initial, you know, tentative, and the hypothesis has to be subject to scrutiny. You know, the way the scientific method is great, because the reason is it essentially acts as a filter. It acts as a filter in the sense that there's something called peer review, and peer review is the filtering mechanism that filters out the bad science from the good science, basically. And so the peer review process is it's a self-policing process. And so what happens is every scientific publication is subject to scrutiny, and so they're going to look for holes in the whatever your conclusions might be from that particular paper or whatnot. And so everything's subject to that. And so the scientific method is good. So the hypothesis has to be subjected to that scrutiny. And once it is, and once it becomes generally accepted, then we have the theory. And so the theory, that's not to say theories sometimes aren't subject to scrutiny. Theories are always subject to scrutiny. You know, if there's if theory predicts something, you know, and it doesn't materialize, then there's something wrong with the theory, or there's something wrong with nature. No, there's something wrong with theory, you know. This is what the big thing with the Large Hadron Collider, you know, you have the theoreticians predicting stuff, and then you have the experimental people trying to see, you know, is that what they get, or what do they get when they do these things? Yeah, the other thing is the predicted new observation. So that's what I was looking for. The other way the law was derived was it was derived theoretically. What law was derived theoretically versus empirically? What was the name of the law that was derived theoretically versus the law that was derived empirically? Atomic theory was derived empirically. Atomic theory came from the observations that, well, what observation or what law did atomic theory come from? You know, these are things that should be quick on the recall, but obviously it's only been one day. But if it's one day, you know, when do you learn it? You know, So the best thing to do is learn it that day. So this is why I gave you a homework assignment. The homework assignment was to go back through your notes and make sure you understood everything in the notes. That was your homework assignment. That's your homework assignment for every day. You know, their homework assignment for every day is go back through your notes and make sure you understand everything. Because if you understand everything in your notes completely, then you should get an A in the class. It shouldn't be that difficult to get an A in the class. Yeah, the law of conservation of mass, that led to atomic theory. So if you think about Dalton, when I think about Dalton, I think, wow, you know, that's pretty impressive, because you're going to have skeptics. You're going to have skeptics saying to Dalton, yeah, I don't believe in atoms, prove that atoms exist to me. And so what did Dalton use? What evidence did Dalton have that atoms actually exist? Well, Dalton didn't have all the modern instrumentation we have nowadays, like scanning electron microscope, X-ray diffractometers can generate pictures of atoms and stuff, molecules and stuff like that. He didn't have that stuff. What did he have? He had the law of conservation of mass. You know, is that a very strong argument for the existence of atoms? You know? And so what we did was we used the theory, you know, Dalton's atomic theory in that sense. Well, Dalton's atomic theory has been modified since. You know, it's like theories don't necessarily stay static, but they become better elucidated. And so Dalton's atomic theory has evolved over time, and then we still have modern day atomic theory. You know, when it gives a good visualized, good fundamental description. The good fundamental description is what we saw with the mercury 2 oxide, or the mercuric oxide. When that was decomposed, we could see how the atoms were rearranged in that particular decomposition chemical reaction. That decomposition chemical reaction was called as a redox reaction. In that particular redox reaction, we could see how the atoms were rearranged. So that makes sense versus the competing hypothesis at the time. What was the competing hypothesis at the time of Dalton?
We could possibly like print out one that shows that like the positive from the
All right.
Yeah.
Yeah, that you can divide an element infinitely. Yeah, if you divide the element infinitely, then could you come up with the law of conservation of mass? So let's say you were a proponent of the opposing hypothesis. You know, are you convinced? You know, can't you argue the same thing? I mean, if you could divide an element to an infinitesimally small piece, wouldn't the law of conservation of mass still exist? And so you have to think about these, you know, these arguments against. And in fact, when you do scientific publication, you're always thinking about that. You know, you're always thinking to yourself. You know, you're your own critic in terms of, you know, does this hold up? You know, could this withstand scrutiny? That sense. And the scrutiny is not people trying to be mean, although sometimes it might sound like it, you know, when they're tearing apart your paper or whatnot, you know, they're just trying to, I mean, this is just how science works. There's no real, there's not supposed to be any kind of real attack in that sense, personal attack on it, just attack on your science. That's fine, which is fine. That's how it should be. All right. So anyway, going back through this is what you do. You know, after, let's say, after you read day one's notes by the 20th time, you know, this type of stuff comes very fast because it's, you know, you've seen it so many times, basically. I know it's only been one day, so maybe it's not quite in there yet. But this is the types of things. And then you write little notes, you know, what was the take-home message of this? You know, what was the point? Sometimes I don't give you a take-home message or the point. What was the point of the last 15 minutes? So that's what you do. You know, what you're going to do is you're going to look at that information and go, okay, this is what I got from this, you know, and this is what I need to know. And so that's your study guide, basically, right there. All right, the law of multiple proportions is a little bit different. What was the law of multiple proportions? Where did that come from? Was that derived empirically or was that derived theoretically? Now, the laws don't really give us a fundamental description. The law is just some pattern, a mathematical pattern. And so, we use the laws just to make predictions, simple predictions. So, okay, Kazra. So the law of conservation of mass was found by predicting new observations. No, not the law of conservation of mass. The law of conservation of mass was not predicted. The law of conservation of mass just came from observations. You know, when you look at Lavoisier's experiments and other people's experiments, including this experiment. Let's take a look at this experiment here. It just came from observation. So let's hear.
2 beakers containing lead nitrate and potassium iodide sit on a balance. They are mixed and a reaction occurs. Does this reaction conform to the law of conservation of matter?
So let's see what the mass was at the start. And so this is a balance. This balance, okay, 99.344. So
Balance.
this balance is really sensitive. It reads to 3 decimal places. So it reads to, this would be the tenths, hundredths, thousandths. So it reads to the nearest thousandth, 1/1000th of a gram, or the nearest milligram. We call this the milligram position here. We have balances, and in Chem 4, our balances only read to the nearest hundredth. And so we can't get milligram precision with our balance because this digit's missing here. In Chem 1A, we have balances that read 1 more digit. And so if this reads to the nearest milligram, in Chem 1A, we can get it to read to the nearest tenth of a milligram here. So 99.344 was the mass at the start. And at the end of this reaction, oh, so that's the wrong reaction, sorry. At the end of this reaction, 99.343. So it looked like we lost a milligram of mass because we started at 344, now we're at 343, but there's some slight error, you know, because of the way this balance has to operate. So for example, we could have a situation like that, you know, like, is that number what we call exact? No, there's a little bit of uncertainty in these measurements, and let me tell you, it doesn't look so uncertain. You know, when you have a reading of 99.344, what does that mean? Does that mean that weighs exactly 99.344 grams? No, it doesn't, because the way the electronics works here, let's say the actual weight, you know, if I see a mass like this, then the actual weight could have been something on the high end. The actual weight might have been something like this. It could have been 99.3444 grams. Let's say that was the actual weight, but this balance can only display 3 digits. So what the balance is going to do is it's going to knock off that 4. And so what we're going to see on the balance readout or the balance display is it's going to read 99.344 grams because it can't show that. This would be 4/10 of a milligram. On the low end, let's say the actual weight was 99.3435. Well, it's not going to show this 1/10 of a milligram position. So what the balance electronics will do is it's going to round it. And so the balance automatically rounds this to 99.344 grams. So what happens here is something like this. You know, let's say I'm at this low end here, 99.3435 grams. And so the difference between seeing a readout of 99.344 grams versus 99.343 grams could be down to just 1/10 of a milligram. Because if I just, if there's just 1/10 of a milligram off here, that could drop it to 99.343. And so a fluctuation like that, although, you know, I'd rather not see it, means, you know, there's a little bit of random error in this, and that could account for that. It's not that we lost mass. The other, well, it could be that they lost mass. The other thing that could have happened is this, and I didn't watch that carefully, but the potential thing that could account for that mass difference, I'd do this, actually I'd do this one again because of this. Okay, the person has these, those look like vinyl gloves. You know, vinyl gloves aren't very good. Vinyl gloves are usually used for food preparation, and they aren't very good for chemical resistance usually, but maybe for these, it's okay. One of the things could be that some liquid spilled on the side and got attached. You know, you can see a drop of liquid there. And so maybe, maybe their glove picked up a little bit of liquid. Tenth of a milligram isn't much. A milligram, okay, think about, you know what a milligram is? A milligram is something like this. If you take a dollar bill, and you say a dollar bill is a gram, okay, divide that dollar bill into 1,000,000 pieces, and one of those pieces would be a milligram. So to be off by 1/10 of a milligram, okay, now take that, okay, take that dollar bill, divide it into 1,000,000 pieces. Actually, that would be a microgram. Sorry, divide it into 1,000 pieces, and then take one of those pieces and divide it into 10, and then that would be a tenth of a milligram. 1,000 pieces. Sorry, microgram would be 1,000,000 pieces. Well, anyway, so we would say conservation mass is observed here for this. And so you do a whole bunch of experiments, not just the ones Lavoisier did, but a whole bunch. And that's why we get a law, because we see this consistent pattern. And based on that, that's where we got the law of conservation of mass. Let's see if it works in the next reaction here. It's lead to iodide. The next reaction is going to be hydrochloric acid and sodium carbonate right here. So let's try that.
2 beakers containing hydrochloric acid and sodium carbonate sit on a balance. They are mixed and a reaction occurs. Does this reaction conform to the law of conservation of matter?
All right, when we look at this second reaction here, the final mass is 88.049 grams. The initial weight or mass, what happened here? Is it not working? Is
Carbonate
96.9, and so we definitely lost a lot of mass. So is this a violation of the conservation of mass here? It appears to be. So you might be the skeptic who goes, wait a minute, you know, I don't believe in your conservation of mass, the law of conservation of mass, because I've found an exception. Well, what would you argue in this case if you were a believer in the conservation of mass? Somebody says, well, I found an exception to your law, therefore maybe we shouldn't call it a law. You know, maybe the loss of exceptions. Did we find an exception to the law of conservation of mass, or am I missing something? And so this is why you need, because sometimes everybody gets trapped in this thing, you know, tunnel vision or whatnot. And so you need outside eyes to scrutinize. Yeah. So Kazra, no, some of the solution got released. Okay, you wouldn't call it a solution because the solution in this case would be the liquid. So did some of the liquid spill out? It looked like, you're right, it did look like some of the liquid spilled out, but when we weigh things, everything on top of this metal plate is going to be weighed. So even if some liquid spilled out of here and fell onto the plate here, the mass would still be accounted for. The previous thing was if some liquid spilled out and got onto this person's gloves here and then got removed, then we would have lost some matter. And so in this case,
They are mixed and a reaction occurs.
oops, it's hard to control this video. Okay. It did look like some might have spilled over, but it didn't look like it spilled onto, you know, the side.
Does this reaction conform to the law react?
Didn't look like it spilled out to the side and off the pan. This is called the pan, the metal plate there. Okay, heat doesn't have mass necessarily. Heat, but you're getting closer. Just keep going. It was released as gas, right? Do you see the bubbles of gas? This
Does
is called.
this reaction conform? They are mixed.
You know, this thing is kind of frustrating because it doesn't let me pause. Do you see the gas bubbles there? That's called effervescence. You know, it's like a soda. And the gas weighs. You can feel like, even though you don't necessarily feel it, it feels like gases are weightless sometimes, but gases weigh a lot. I mean, at sea level, you know, the atmosphere weighs about almost 15 pounds per square inch. This is why, you know, in the ultra high vacuum stuff that I was showing you earlier, they had to build it like a submarine, really thick metal walls, really thick glass windows, so it doesn't collapse, you know, because the air weighs a lot. And so the CO2, if we could capture all that CO2 that gets evolved and weigh it, then we would see that we didn't lose any mass. And so conservation of mass. And so they should have had a closed system. A closed system is where nothing could escape. And so we capture all the CO2. And then, now weighing gases is tricky, you know, a bit more tricky, but it's easier for compressed gases. Let's say you go and buy a helium tank for filling balloons. You know, when helium feels like it weighs nothing, but when you have a helium tank, you know, full versus a helium tank that's empty, you can easily tell the difference because a full helium tank weighs a lot more than an empty helium tank. And the same thing goes if you're a scuba diver or something like that. Empty tanks are a lot lighter than full tanks. And so you can actually weigh the gases. That's just a bit more tricky. When you buy gases, you buy it by the gram. That's the easiest. You don't buy it by, you know, when you go out and buy gases, it would be ridiculous to buy it by the volume. Because, you know, the tank could be empty. You have let's say you have a 100-liter tank, it could be completely empty. I'll talk about what empty means later, but it could be completely empty, or it could be filled. You know, the gases can be compressed or it can be expanded. So if you really want to know how much gas is in there, then you want to know, you know, the weight, the mass of the gas. So if you have 1,000 grams of gas, at least you know you're getting a full 1,000 grams versus if you have 100 liters, you could put, you know, 10 grams in there or 1,000 grams or 10,000. Well, I don't know if you get 10,000 grams, it would be too much, but, you know.
Reaction occurs.
So anyway, this is the type of scrutiny that
Does this reaction conform to the law of conservation?
Now we don't always, you know, like for example, Lavoisier didn't take this all the way to theory. You know, Lavoisier ended here with this kind of law of conservation of mass because he took very precise mass measurements, and he did a closed system. If you look at his apparatus, it was all closed. And so Lavoisier took it here, and then maybe 100 years later down the road, or less than 100 years later, then Dalton took it from here to atoms, you know. And so it's a progression, you know, it's the scientific method. We work on different parts of that, of the steps of the scientific method. But this is the law of conservation of mass. Here. I talked about the first law of thermodynamics. Can somebody remind me what the first law of thermodynamics stated? You go, well, first law of thermodynamics, this is not a physics class for one thing, and then, yeah. But it's not hard because the first law of thermodynamics, if you see it so many times, you see it like 50 times and it becomes pretty easy. Yeah, energy cannot be created or destroyed. That's right. Energy is conserved. That's good. And so we have the first law of thermodynamics here is also called the law of conservation of energy. So this is at the end. And so eventually, you know, we use energy, but what happened to that energy? So we use energy to power your range, or you use energy to generate electricity. You know, and so it seems like we use a lot of energy. And so it seems like we're destroying a lot of energy, but it's kind of weird because, you know, the energy, like for example here, this person's using energy to push this, you know, bar down here and generate the generator. And so they're expending a lot of energy, you know, pedaling this thing here. But where does that energy go? Does that energy just disappear because you used it up? No, the energy gets converted into a different form of energy. And so one of the biggest examples is this. When we look at a chemical reaction like this, we look in terms of two types of energy. What two types of energy do we look at when we're looking at the total energy of something? So let me go here with this. Let's say I have methane. Does anybody remember the formula for methane? Close. NH4 is close. CH4 is correct. Let me go to a different color here. I don't want orange. It's just black. CH4 is methane. And one of the chemical properties of methane is what we call a good reducing agent. And good reducing agents like to burn or like to combust. Oxygen is what we call a good oxidizing agent. And so this is what we call a redox reaction, where we have a good reducing agent. Reducing agents are also known as fuels. So we have a good fuel here. And if we have a good fuel here, we need an oxidizer, like oxygen. And then I need two oxygens because what I form in this particular redox reaction or combustion reaction here is CO2, which is a gas, and H2O, which is liquid. And so when I rearrange the atoms, you know, to get them to match, I have to put these two. So I need two O2s and two waters to get the atoms all, so I don't lose any atoms. In the conservation of mass, we don't lose any atoms, we don't gain any atoms. The atoms are all rearranged. So over here I have one carbon atom. That one carbon atom gets rearranged into CO2. Over here I have 4 hydrogen atoms. Those 4 hydrogen atoms get rearranged into water here. If I have 2 waters, I'll have a total of 4 hydrogen atoms. Then I have a total of 4 oxygens. Now 4 oxygens are mixed. 2 of the oxygens end up in CO2, and the other 2 oxygens end up in the 2 waters over here. And so all the atoms are present and accounted for. So we have the law of conservation of mass and a balanced chemical equation. This is called a balanced chemical equation. A balanced chemical equation shows that no atoms have disappeared, no atoms have magically appeared. And so we need this balanced chemical equation. We also like the states in here. It's good to know the states, like methane's a gas, and then O2 is a gas. CO2 is a gas and H2O is a liquid. H2O is a liquid at 25 degrees C. And 25 degrees C, we call what? 25 degrees C has a special name that we call what? Room temperature. Good. And so a lot of people just say RT, RT standing for room temperature. And so if we do this at room temperature, so well, how can we do this at room temperature? Because when you burn methane, you know, on a stove, it gets very hot. Yes, it gets extremely hot. And so what we're looking at here is we're looking at the initial mixture, okay? The initial mixture, this is called the reactants. And the final mixture, what's the final mixture called in this? You can go off the mic if you don't want to type too. You can just say it. Products, good. It's called the products. But what happens in going from the reactants to the products? Well, you get a flame. What the heck is a flame? Yeah, it's more than just heat and energy. There's more to a flame than just heat and energy. But it's good. There's a lot of heat. There's a lot of energy in a flame for sure. High energy. When you have high energy, you know, things are moving fast. Things are moving fast. You have high temperature. So flames also have a very high temperature. So this is the skeptic in me is saying, you know, why am I saying at 25 degrees C? It's not, certainly a flame is not at room temperature. Certainly a flame is very, very, very hot. Like closer to what? Well, what did I give you as a ballpark estimate for the temperature of that flame? I don't know if anybody wrote it down, but these are the types of things that you could get caught off, you know, like you don't know on the test, you know, maybe the professor might ask you something like that and you might not think it's fair, but if you know it, it's better than not knowing it, you know. And so did anybody write down what I told you the temperature of the flame was roughly? Just ballpark. Is a flame 1,000,000 degrees? Would you say a flame is about 1,000,000 degrees, true or false? Million degrees C. How about 10,000? Would you say a flame is 10,000 degrees C, true or false? Actually, it's not, that's good. You want to take a guess, but it's not true. It's false. That's false. And so what is a flame ballpark? The methane flame ballpark. 1600 is too hot. You can get flames up to 1600, but you're going to have to use a different gas than methane. 1600 is like I used to work in the laboratory where we had an electric furnace that got up to 1600 Celsius. 1600 is a very significant number. I know 1600 degrees C very well because that's 1600 degrees C is the melting point of platinum. And this furnace, this electric furnace that we had was made out of platinum wire. At the time, platinum was a lot cheaper than it is now. That furnace is worth a small fortune now. I mean, I can't imagine how expensive that furnace must be in considering today's price of platinum. But pretty much that's one of the hottest furnaces actually it was the hottest furnace that you could buy, electric furnace that you could buy. And so I use that quite a lot, and there's lots of platinum in there. Other metals, when you get to high temperatures, metals tend to oxidize quite rapidly, you know, because you got oxygen around. Metals will oxidize quite rapidly. But 3,500 is still too hot, and 3,500 Fahrenheit and 35 C, it was a bit cooler. And so the point of this is, you know, you never know what's going to be asked on exam. So that's why I try to get as much information. And the thing is, you go, oh, okay, what's the purpose of memorization? You think it's useless, but the purpose of memorization is you need some kind of reference framework, you know, some kind of reference framework. Oh, that's really hot. Well, somebody might ask you, how hot is that? You know, oh, it's super hot. Well, what is super hot? You know, and so what you got to have is you got to have some reference points. Those reference points, we got to memorize those. That way we can talk more in more detail about certain things. You know, how hot is that? You know, more specifically, what can that amount of heat do? And so you might think, that's not relevant, but these types of things. And there was this very, very big push away from memorization, but you can't really do chemistry without doing some memorization. Otherwise, you don't have any idea what these numbers mean. You know, these numbers are just numbers you punch out in the calculator and you get some number on the display and you write it down, but they're utterly meaningless numbers. You can't have meaningless numbers. The numbers have to mean something, and you have to put those numbers in some sort of perspective. And so this is why we need some kind of framework. But I can imagine, you know, not everybody wrote it down, but, you know, if there's a not that I would, you know, I probably wouldn't because, you know, I try to be a little bit more reasonable, but, you know, at UCLA, I would be prepared for something like that. You know, I would expect a question, you know, about some obscure little thing that the professor said that, you know, I'd have to have recalled. And I would have known that number by the time the final hit because I would have had 10 weeks of going through and having it memorized by then. This is a repetition. But anyway, I said about 800 degrees C. Initially, I said 1,000. I said 1,000 degrees C about 3 times and then finally dropped it down to about 800, which is a little bit more accurate for that flame. But just to show you, this is, you know, this is one of the things that I really worked at doing. I try to make sure, you know, my notes were as complete as possible. That way, you know, I didn't have any problem with the recall of information. And so certain classes, when I was a student at UCLA, certain classes allowed me to record the lecture. Most classes I couldn't record the lecture because the professor didn't want the lectures recorded. But the classes that I was able to record the lectures, I thought that's going to be an easy A because I'll have everything. I won't miss a thing with a recorded lecture. And that it turned out to be true. I took history of French film there at UCLA, and the professor there, she allowed, you know, us to record her lecture. She never wrote anything on the board. She just stood at the podium and talked and talked and talked. And so I remember, you know, before I would just, sometimes I'd go to sleep listening to the lecture and thinking, oh, maybe this is going to go into my subconscious, so I don't even have to think about it. And it's kind of weird. Maybe it did, because it turned out to be, you know, everything on the exam was pretty much everything she said. In her class, it was 100% of the stuff on the test was stuff from the class. There was nothing really beyond that, beyond what she said. So I just, that was one of the easier classes I took there. Anyway, going back to this, you know, you miss a lot of information when you do take notes. So it's good to go back and through, and it's good to compare with friends in the class to see, you know, I used to do that as well, to see if I missed anything important. But going back to this question here, you know, we talked about the flame. And so in going from here to here, we have a flame, and that flame is like 800,000 degrees C. Why am I saying at 25 degrees C? The reason I'm saying at 25 degrees C is that flame doesn't last forever. What's going to happen is this. We're going to start off at methane and O2 at room temperature, and then we're going to combust it in the plasma. The flame is a plasma. Plasma is a super hot gas, so there's a lot of heat, there's a lot of energy. And what happens in the plasma is there's super high speed, high energy collisions. And these collisions result in pieces of the atom breaking off. And the typical pieces of the atom that break off are electrons. You know, electrons break off, and when electrons break off, we form free electrons and charged atoms, which are called ions. And the sun is a plasma, so there's a lot of free electrons in the sun and charged atoms, hydrogen atoms. And so that's what the plasma is. We'll talk more maybe about plasmas later, but anyway, that plasma doesn't last forever. The flame doesn't last forever. Eventually what's going to happen is everything's going to react, and then we're going to end up with products, the products being CO2 and H2O. There's a whole bunch of intermediate stuff happening here. But when we do this, we only look at the initial state and the final state. And so the initial state and the final state. We don't look at how it got there. And so initially, we do look how it got there, but when we're looking at energetics, like I did earlier, we're just looking at the initial state and the final state. The whole intermediate step, we're kind of ignoring, but lots of chemists are very interested in that. And so when we look at the initial state here for methane, what's a more stable mixture? You know, these two mixtures don't have the same energy. And so here I'm going to put this, use the symbol for what? Okay, well, that's actually, let's see, I've been talking too long here, but we're going to take a break right now. Let me pause the recording. It's time for our break, and then we'll take like a 15-minute break. Then we'll resume after that. All right, so the question I left off with is U. What was U again? Let's see, we have a chat window here. Okay, U, actually, heat, there's some symbols here. And it takes some time. And the symbols aren't always consistent. But one symbol that's pretty consistent is Q. Q is for heat. Heat is usually a transfer of energy from a hot body. When we have a hot body, what temperature is kinetic energy. And the higher the temperature, the higher the kinetic energy. And so heat is usually a transfer of kinetic energy from a hot body to a cool body. And so things feel hot to the touch. If you're both at the same temperature, then one object's not going to necessarily feel hotter. It's energy, Carlitos, or more specifically, Kazar has it, it's internal energy. But what the heck is internal energy? It's not mass, although mass and energy are related. We'll talk about that pretty soon. But internal energy has another name. What is the other name for internal energy? You know, these are part of the connection things that you want to think about. Well, potential energy is part of internal energy. Total energy, that's correct. So it's total energy, that's good. It's the total energy of that. And the total energy is going to have two components to it. One of them is potential energy. And there's one more component to the whole energy. What is the other component to total energy? It's the kinetic energy. So when we're looking at the total energy of methane and oxygen deals with its kinetic energy. You know, the kinetic energy, well, it's at 25 degrees C. That's its kinetic energy, essentially. You know, the temperature, actually, what we call the absolute temperature. Absolute temperature is proportional to its average kinetic energy, and so that's it. So if it's at 35 degrees C, it's at a higher temperature. It's at a higher kinetic energy. And the CO2 in the water. What we're going to do is we're going to burn this, and then, you know, we're going to make CO2 and water. And eventually that CO2 and water is not going to stay hot forever. You know, initially it's going to be very hot because you got the flame. But if you give it enough time, it's going to cool down. As it cools down, what happens is it releases that heat to the surroundings, the environment. You know? And so as it releases the heat to the surroundings, the CO2 and the water cool down. And eventually everything cools back down to 25 degrees C. So what we do is we do this. We start off the reaction here at 25 degrees C with this mixture, and then we end the reaction here at 25 degrees C with this mixture. You know? And so both of these mixtures, the reactant mixture and the product mixture, have the same kinetic energy because they have the same temperature. That's what we talked about yesterday. So what's the different? You know, if these have the same kinetic energy, then what's different between these two mixtures is the okay, yeah, you're right. One is lower, one is higher. That's true. One of these mixtures is lower and one of these mixtures is higher. Which one do you think is higher energy mixture? The methane and the oxygen, or the CO2 and the water? The CO2 in the water, Nisa? Is higher in energy or lower in energy? You say CO2 in water is higher in energy. Higher. Okay, CO2 in water higher. And what makes you think it's higher in energy? And what would the argument there be? You know, it's higher in energy because, what's your thinking there? Let me see. Let me check something here. Okay. You can go off, if you want to go off mute, just hit the space bar and you can talk. It's higher in energy because it combines with oxygen, okay. Any other thoughts on this? So does everybody agree that CO2 and water, this mixture has higher energy than methane and oxygen? Or, actually I should send out a poll. Yeah. Let me see. No, it's lagging. I have to log into Zoom web. I'm not going to send out a poll. Or don't know, you know. How many of you don't know which one is higher and which one, or can't tell which one's higher and which one's lower? Okay, don't know, not sure. Okay, I'm going to give you an easy way, I think, to tell which one's higher in energy and which one's lower in energy. Okay, let's say if you could fill up your bedroom, what would you rather have? Would you rather have something like CO2 and water, which would be like carbonated water or sparkling water, maybe CO2 and water. Although, you know, CO2 and water, they don't really mix, so there's bubbles, or maybe the CO2 is on top of the water. So if you have a tank or a container full of CO2 and water, or let's just take one. If you buy sparkling water, that's CO2 and water, basically. So if you have a bottle of CO2 and water on your shelf versus a bottle of methane and oxygen on your shelf, would you treat those two the same, or would you treat them a little differently, you know, or it really makes no significant impact differently? Well, in what way would you treat them differently? You know, if you had a bottle of methane and oxygen, the bottle of sparkling water, I would treat the oxygen and methane with more care. Why would you treat it with more care? I mean, because if it's more stable, then you wouldn't have to treat it with more care. If it's more stable, you should treat the sparkling water with more care, because, you know, if you shake up the bottle of sparkling water, what might happen? If you shake it up, you know, and you open it, it might spray out all over the place, right? And so isn't CO2 and water more dangerous than, I would think so, because if it sprays out all over the place, then it's more dangerous than methane and oxygen. And, you know, obviously, you know, that's not the case. In fact, it was just not long ago. Every year, do you know every year how many people die from natural gas explosions? You're right, it has more energy. Methane and oxygen is potentially very dangerous. It's a very dangerous mixture. In fact, there was a pretty spectacular explosion and unfortunately resulted in deaths. I think it was last year or the year before, but there's since been other explosions that have resulted in deaths. But this one was particularly story apartment. Whoops. This is pretty recent explosion, the misspelled apartment, but NYC. Let's see if we can find it anyway. And is this it? This person installed an illegal gas line that led to the blast. Maybe this was it. Yeah, this was it. This was amazing. My God, this is the yeah, and unfortunately, two people were killed in this one. Jerry-rigged gas line. I wonder if they had the before and the after picture. There's nothing left. This is the after. That used to be a 5-story apartment building, and unfortunately, these people lost their lives in the blast. But it happens every year. People are killed in methane explosions. And so, what's the difference? The difference is potential energy. You know, methane and oxygen is a very explosive mixture. Yeah, carbonated water might be, but that's nothing, you know, compared to methane and oxygen. And so what we say is, even though the kinetic energy is the same, they're both at room temperature, the potential energy is quite a bit different. Methane and oxygen has the potential to violently explode and level. And it pretty much leveled that 5-story apartment building up at the end of that. And so we say that methane and oxygen has higher energy, total energy or internal energy, than CO2 and water. So in this chemical reaction, and this is a chemical transformation, you know, we're rearranging the atoms. And it turns out there's a big difference in energy between these compounds here. This is the element, but these 3 compounds in the element. And so energy is conserved. And so if we go from a higher energy mixture here, and this is going to have higher, you know, we call this U, or energy initial. This is going to be, U initial is going to be the kinetic energy initial plus a potential energy initial. And then U final here is going to be the kinetic energy final plus the potential energy final. And so we're going to have a change in energy, and that's going to be given as delta U here. Delta U would be the change in total energy, is going to be the change in kinetic energy. Well, what was this change in kinetic energy? Well, eventually that's not going to stay hot forever. And so initially we started at 25 degrees C, and then we wait for everything to calm down and cool down, and then that's going to release the maximum amount of energy. When it's still hot, there's still energy that can be released from the reaction. So we just waited for it to come back to the same temperature that we started, and then the maximum amount of energy has been released. And so, well, if we start at 25 degrees C and we end at 25 degrees C, what is delta KE? What's the change in kinetic energy? Somebody remind me. Yeah, 0, good guys. And so there's no change in kinetic energy. All the change was in potential energy. So we went from a very explosive mixture to a very stable mixture. And so this change in potential energy here is what we're seeing. And this is what we call chemical potential energy. We also have gravitational potential energy. Gravitational potential energy is maybe a lot easier to visualize. You know, if you're at the top of a cliff or something, you're at high gravitational. You don't want to fall to the bottom of the cliff. You know, if you fall to the bottom of the cliff, then you're going to lose a lot of energy. The problem is energy is conserved, right? It would be great if you could just jump off the cliff and then energy disappeared. Then you can just land gently here. But what's going to happen is if you jump off the cliff, you're going to go from high gravitational potential energy to low gravitational potential energy. And unfortunately, that energy has to go somewhere. And usually that energy goes into work here, maybe some heat. You know, it depends if you're sliding on your butt down the cliff or what. But the work is probably going to go into work and mechanical work of breaking bones and causing other injury, bodily injury, because energy is conserved. The energy just doesn't disappear. It's got to go somewhere. And so the same thing here, when you burn this methane, that energy has got to go somewhere, and that energy goes into either heat, Q, or W. What was W again? W was a symbol for work, right? And so heat and work. So that's what they're showing here. You know, the energy is just being transferred. Eventually, you know, the energy, yeah, we're using the energy, but when we're using electric energy here, we're converting that electric energy. What happens to your TV set, you know, or your range? Or actually range, you want this to happen, but what happens to your TV set? You're using electricity here. Does that well, what happens is that electricity gets converted into other forms of energy, like light. You know, we want lots of light to be. Light is electromagnetic radiation. So we have some of that electricity gets converted into light. And so making light is work, you know, to make light. And also this TV might start getting hot. If it starts getting hot, then we're going to dissipate that energy as heat. So the energy, yeah, we're using electric energy, but the electric energy doesn't disappear. It's just being converted into work of the light generation and heat here. Work, we have many different kinds of work, and this work is just the sum of all work, you know. As far as work goes, we have work of mechanical work, like lifting or spinning or rotating. This is mechanical. We have work of electrical generation, you know, electric work, etc., etc. Noise, making light, etc. And so that lots of different forms. So law of conservation of energy here is that, and so this is just showing it. What the most chemical potential energy is one of the most efficient ways of storing energy, in terms of chemical potential energy. So we could store the methane and the oxygen, hopefully no sparks around or no hot surfaces to get it to ignite, no flames. And so that's a good way of storing energy. Batteries are another good way. Batteries are storing chemical potential energy. There's a chemical reaction that happens. This is called a redox reaction. In batteries, we have another redox reaction. This is just storing chemical potential energy here in the battery. Storing heat is not very efficient, in terms of energy goes. Storing electricity, it's very hard to store electricity. You don't store electricity. You use electricity to generate a chemical reaction to store the energy as a chemical potential energy. Batteries are not storing electrical energy, they're storing chemical energy in batteries. Okay, that's actually the end almost of this. And normally this is where we stop, but your book goes on a little deeper than this. A little deeper than this is that it turns out that there is a slight, there's a very, very slight deviation from the law. When you do ultra precise mass measurements, unfortunately, we don't have the precision, like, a tenth of a milligram is not enough. When we do conservation of mass for a reaction, we don't see any mass changes. Like here, there'd be no mass changes. But if we had a balance that could measure out, measure out to the smallest amount of grams, so this would be milligrams here. So this would be the milligram digit. This would be the microgram digit. This would be the nanogram digit. Actually, I don't know how many we'd have. This would be the picogram digit. Do you know what comes after pico? This would be the femtogram digit, And so if we had a balance that could measure to the nearest, let's say, femtogram, we might be able to see it. But there's a very, very slight mass change here, extremely slight mass change. Actually, if we do nuclear chemistry, now nuclear chemistry plays by a different set of rules. What rules does chemistry abide by? And when I say rules, what force of nature is most important to chemists? The sun, Yeah, the sun is a source of energy, you know, but it's not, you know, the sunlight, of course, sunlight is going to be very important, you know, for many things. But, you know, if there was no sunlight, would there still be chemistry? And the answer is yes. Yeah, there'd still be chemistry. So there's something else. You know, sunlight's a great source of energy for our planet and for life. You know, we need photosynthesis. And there are other, what we call photochemical reactions, you know, that are important. But I'm talking about what force of nature is most important. These are the rules, you know, when chemists think about, you know, what rules dictate the laws of chemistry, you know, what rules dictate the theory of chemistry, you know. What rules in physics, what rules of physics, you say. Or what force of nature are of most interest to chemists? The measurements are, you know, regardless, you know, measurements are, they don't really dictate. Like, if you didn't measure anything, chemistry would still go on, you know, and let me scroll up here. So measurement, gravity. It turns out, are chemists really worried about the difference between weight and mass? Not necessarily so much. You know, weight and mass are different, but chemists don't worry about it because gravity is not significant. I mean, gravity is significant because it holds us down on Earth, but it doesn't dictate the way, you know, chemicals behave. You know, when we're looking at the properties, you know, chemists are interested in properties, right? And they're interested in what about properties, you know? Well, what do we correlate properties to? Structure and composition. So when we're thinking about structure and composition, what types of things dictate that, you know, what force of nature really, when we're thinking about the forces of nature. Are there any other forces of nature that I mentioned in class yesterday? Actually, there was one other force of nature I mentioned in class, and that's the one I'm looking for. I'm just saying if anybody remembers it. You want that fast recall because, like I said, the exams at UCLA and UCs are typically timed. They're very, like, you have 50 minutes. 50 minutes is very short, except for the final exams. Final exams at UCLA are 3 hours. It's 3 hours is still too short for some of those finals. And so you need speed. So how do you generate speed? You know, a lot of people say, you know, speed, it's ridiculous to grade on speed. You know, it's ridiculous to grade on speed. You got all different kinds of opinions about that subject, but you're graded on speed. You got to be fast. You know, if you want to do really well, you got to be fast. How do you get fast? You have to have very fast recall. And how do you get fast recall? It's like training. You know, if you want speed, let's say you're into some sport, you know, or some video game, you know. Yeah, how do you get fast? You train. You train. It's like if you want to get good at exams, you train for the exams. It's just like any other sport. You know, people go practice basketball all the time. They're practicing. Why are they practicing? You know, what's the purpose of practice? You know, you might think to yourself, you know, if there's a big game, just wait until the big game and let's go. There's no need to practice. And so you got to think of your studies in the same way. You know, you're the academic athlete, although academic athletes, you know, they don't get any you know, or for the most part are largely ignored, but you know, it's the same kind of thing. You got to train for this kind of stuff. If you want to do really well on a test, you got to train for it. How do you train for it? Well, you do this kind of practice stuff. You know, if you want to shoot a basket from here, you got to practice shooting a basket from there, you know. If you want to answer questions like this, you practice answering questions like this. And then pretty soon you can do all kinds of tricky combinations. Well, pretty soon you can do all kinds of tricky combinations at solving problems too, you know, if you practice enough. Problem is nobody practices. Nobody thinks it's important to practice. You know, it's like playing the piano. You know, oh, okay, I watched a YouTube. You know, this is how you play Chopin. I watched some pianists play Chopin, and then you don't think about it, and then 3 months later you have to do your concert, and you go, oh yeah, I'm just going to cram it in one night, learn how to play Chopin, and then do my concert the next day. You know, that's the way a lot of students think, and it blows me away that, you know, they could do so much better, you know, so much better if they just committed a little bit of practice to it, a little bit of extra time. And so this is the daily homework that I have for you guys, is to go back through it. And a lot of people think, oh, that's a waste, but is it a waste to go practice shooting baskets? Is it a waste to practice playing the piano before some concert? No, you know, and I don't understand why people don't think of this in the same way. It's always something that has always been a disconnect for me. So how do you get fast? You know, you practice. So what was the force? Well, the first thing is you got to make sure you're not missing any information. So did somebody get the force? Somebody should have gotten the force, because we did talk about it, but it's just making the connection. How do you make the connection? You got to think, well, what was the point? And what was the whole point of talking about certain things, you know? For example, what was the point of talking about Coulomb's law? The point of talking about Coulomb's law, these are little annotations I write myself. The point of talking about Coulomb's law is to better understand electrical forces. Well, what's the point of better understanding electrical forces? You know, how electrical forces operate. That's why we talked about Coulomb's law. Well, the point of better understanding electrical forces is because electrical forces dictate chemistry. You know, chemistry is dictated by electrical forces. Electrical forces are most important in chemistry, and the rules that chemistry plays by are electrical forces. The rules of electrical forces. You know, gravity is not such a big deal. You know, obviously, yeah, things are going to sink to the bottom, you know, go closer to the center of the earth, but you know, that happens normally. And so we're already accustomed to that. But sometimes things can go against gravity, like the pith ball. You know, if you look at the pith ball that we saw earlier in the earlier slide, this is going against gravity. And so this is more important than gravitational force here. You see this pith ball is suspended. You look how loose the string is. String here is tighter because gravity is holding these two down, but here the electrical forces are overcoming the gravitational forces. So electrical forces are the most important in chemistry. And this dictates, this is how these atoms bond together. I gave you the example of a water droplet. You know, the water droplet shouldn't have just dispersed into a million little tiny droplets. No, this fountain was shooting out big globules. I mean, these were big drops. It's a pretty cool fountain in downtown LA. I forgot exactly where, but it shoots out these gigantic drops. I mean, and these drops, you can watch them, and they're like blobs, and they're all contorting and distorting until they hit the ground, and then they'll disperse. But, you know, what's holding all those water molecules together? Well, I told you what's holding all the water molecules are hydrogen bonds, but what are hydrogen bonds? Well, hydrogen bonds are these electrical attractions, you know, these positive, negative attractions that are holding it together. And so not only did that happen, so these would be like two water molecules being held together. They're kind of sticky. I talked about they're kind of sticky like glue, but it's not like a permanent glue. I said it's not like a super glue. If it were a bond, it would be like a super glue where it's hard to break off. You know, this is just kind of like a sticky molasses or sticky sugar. You know, the hydrogen bonds. The bonds holding the hydrogens to the oxygen, those are like super glue, and those are very strong electrical attractions that hold those together. Okay, so so that type of stuff you want fast recall, because the fast recall is going to help you be able to solve challenge problems for sure. Anyway, this ends chapter 2, so we're going to move on. Oh, it doesn't quite end chapter 2 because there's another set of rules that I didn't talk about. And the other set of rules is what the nuclear chemists play by. A nuclear chemist, for nuclear chemists, it turns out that electrical forces aren't so significant. And what we see here is the law of conservation of mass and energy. So let me delete some of this stuff here. Clear the drawings here. This was really noticed in nuclear chemistry, because in nuclear chemistry there are more significant mass changes. And so let's say when there's a nuclear reaction, well, we aren't doing really nuclear chemistry in this particular class. However, there is some nuclear style chemistry that happens here. And so we don't really notice this, you know, and so normally we just do law of conservation of mass and law of conservation of energy. Law of conservation of energy is AKA first law of thermodynamics. But we have to combine these, especially for nuclear reactions. This is important for nuclear chemistry. Now, nuclear chemists, they don't care about electrical forces. You know, electrical forces are not significant. Electrical forces are insignificant. They look at stronger forces, you know, like nuclear forces for nuclear chemistry. But where we're going to see this happen is like in nuclear reactions. In nuclear reactions, atoms are created and destroyed. Atoms are created and destroyed. In chemical reactions, atoms are not created, atoms are just rearranged. In nuclear reactions, like for example, if we had U-238, this goes to thorium plus helium, you know. And so this is an unstable atom here. And what's really unstable is the nucleus of this atom. Atoms have a nucleus. Do you know atoms, even though they're a sphere, there's some structure to it. And in the center of the atom, in the center of the sphere is a tiny thing called the nucleus. And this nucleus is unstable. And outside of that nucleus are the electrons. And inside the nucleus, we have the protons and the neutrons. And those are the subatomic particles. And so when we look at the initial mass here, the initial mass, and we look at the final mass, they're different. In fact, the initial mass is greater than the final mass here. And so mass wasn't conserved. And so what happened was some of that mass got converted into energy. Here. Here. And so there's a change in mass here. And so that comes from this equation here, Einstein, E equals mc squared. This is a very famous equation here. And so what we see is this energy is going to equal delta m, the difference in mass here, times c squared. C is the speed of light. It's a constant, speed of light squared. C, C is just equal to 2.988, I think. Times 10 to the 8 meters per second. That's how fast light moves. It's about 3 times 10 to the 8. 10 to the 8 is, that would be 300 million meters per second. What it would be. And so we see some mass changes here. Okay, we're not really going to get into these types of nuclear reactions here, but it does impact us here because, for example, the helium atom. Let's look at the helium atom quickly. The helium atom, if I look at that, this would be, let's say, the helium atom here. Inside the helium atom, we have the nucleus. And inside the nucleus, we're going to have, in helium, we're going to have what will we have? We're going to have 2 what we call protons and 2 neutrons inside there. And the protons have a positive charge, and the neutrons are neutral, so they have no charge there. And so inside that tiny nucleus, there are 2 protons, but what's holding the 2 protons together? Well, it's certainly not Coulombic attraction, because a Coulombic attraction is opposite charges. Opposite attracts, like charges repel. And so these are 2 like charges. And then we have 2 electrons out here, you know, outside there are 2 electrons. So what we do is we know the weight of the, this will be 2 times the mass of the proton, and then 2 times the mass of the neutron. And so that gives you the total mass here. If we add it up, total mass of the nucleus. Now, when we weigh the nucleus, nucleus weighs less than the calculated total. And so if we sum up the parts, you know, we know the weights of the individual parts. When we sum up the weights of the individual parts and compare it to the weight of the whole unit, they don't weigh the same amount. It's weird. So if you took a 1 pound rock and another 1 pound rock, what's the total weight of that? Well, it's 2 pounds. But if you take a 1 pound rock and a 1 pound rock and then have those together, the weight comes out less than 2 pounds. Well, how can that be? This is called the mass defect. Because of this mass defect, we don't say mass is conserved. We say mass and energy is conserved, because it turns out that this is not a problem with this. What happens is that energy here is the nucleus weighs less than, well, the missing mass here is converted into energy. So the missing mass here is converted into energy, and this energy is called the nuclear binding energy. Nuclear binding energy. And nuclear binding energy is what holds these 2 protons together, because Coulomb's law says these 2 protons should repel one another, not be held together in the nucleus. Coulomb's law says that like charges repel, opposite charges attract. But something's clearly holding these 2 like charges together, and what's holding them together? The nuclear binding energy. Now the mass difference is measurable. This mass defect, we don't need a sophisticated balance to measure this. This is measurable. It's measurable, the mass defect. It turns out that exothermic reactions should also have a mass defect, and endothermic reactions should have a mass defect too, if this is correct, you know, if this is correct. And it does. But that mass defect is so small, it's negligible. And so we don't notice it in chemical reactions. So the law of conservation of mass and energy is really important for nuclear, but for chemists, it's negligible. The mass defect is negligible, therefore we ignore it. And so we just think in terms of the law of conservation of mass and the law of conservation of energy. We think about that, but the reason why Kropotkin brings this up now is so you don't have to, you know, if you get stuck, you know, on the law of conservation of mass, you know, you might get stuck into thinking that it works for everything. You know, obviously it's great if laws work for everything. That would be great. You know, people, well, going back to the first law of thermodynamics, people have been trying to figure out violations of that for ages, and nobody has come up with any violations of that. Same thing here. But this is to be more complete. And so this is not such a big deal. You know, I'm not going to ask you questions about U-238 going to thorium and helium and energy, you know, and thorium is radioactive itself. You know, radioactive means it's unstable. It's an unstable atom. It can break apart. But this type of stuff's not that important. But you know, let's say you want to really be on top of it. You know, you want to be the whatever, the elite athlete or whatever. Then you want to, how long does it take? You know, after the 50th time of reading this, you have it memorized anyway. How long does it take? It doesn't take much time. The problem is that people try to cram it in one night. When people try to cram it in one night, it's impossible. You know, you can't get months of practice in one night. It just doesn't work. And that was my problem too. I'm the typical procrastinator. I wait until the last minute, but that was causing me too much stress and the results weren't good. And so that's why I changed. Yeah, the nucleus weighs less than the calculated total. That's correct. And that's called the mass defect. Okay. Nucleus weighs less than the calculated total. No. The different elements have different atoms. So for example, helium has 2 protons and 2 neutrons. However, hydrogen has only 1 proton in the nucleus. Lithium has 3 protons in the nucleus. And so the composition of the atoms are different. Since the composition of the atoms are different, the properties should be different as well. Yeah. And so we're going to be looking at that as well. So we'll take a look at the composition and properties. We're going to look at the composition, structure, and properties of atoms. And they'll tell us about elements, you know. Hydrogen's different than helium because it's got different atoms, you know, different composition. All right. That let's see, I probably should save that. I'm going to clear these drawings here. This is debatable whether to put this into Chem 4 or not. This is more Chem 1A, Chem 1B. Go into it in more depth. We don't give it the depth it deserves here. You know, sometimes this is why when I was a student also, another resource are the next level book. So oftentimes what I'd look for is if I was taking one class, let's say Chem 4 class, I'd always be looking at the Chem 1A or the Chem 1B because in Chem 4, they might give it a paragraph, but in 1A or 1B, they might give it a chapter, you know, in terms of discussion. So a paragraph versus a chapter, you're going to understand it a lot better if you get more deeper understanding of what's going on. So oftentimes I looked at the higher level books to help me understand the lower level material, you know, because then the higher level books, you just go into it a lot more depth. So when there was an opportunity to buy or to check out or to go to the bookstore, and just read it, you know, I'd just read certain sections or buy it if there were lots I needed. That will give you an edge as well. It's like training, you know, when you're training for something, you want the training to be more intense than the actual, you know, thing. So if you train really hard, then the actual event won't be as hard. Let's go on to the next chapter here. Wrong PowerPoint, sorry. Going to the beginning. That's weird. Yeah, having a problem here. Yeah, that could be it. I have 2 slideshows going. Let's get rid of that one. Oh, it's actually, oh, it's already time for our next, oh, it's almost time for our next break. Let's see, our last break went to 50 now. So next break will start at 50. All right, these are posted on Piazza here. And so we're going to take a look at chapter 3 next. Chapter 3 deals with measurement and chemical calculations. And so when we're doing measurements, some of the measurements are going to be very big, some of them are going to be very small. So we need scientific notation. So let's get just a short, quick review of scientific notation. So what is the weight of a helium atom? So chemistry calculations and measurements sometimes involve very large and very small numbers. For example, the mass. A single helium atom is tiny. You can't even see it, it's so small. It weighs next to nothing, but it does weigh something. So how much does it weigh? This is how much it weighs. And so if we do this, this is milligrams, right? This would be micrograms. This would be nanograms. This would be picograms. Do you know what's smaller than pico? This would be femtograms, and that's where my knowledge ends. I don't know. I don't know beyond femto. You know, a milligram is 1/1000th of a gram. A microgram is 1/1 millionth of a gram, so this is a millionth. A nanogram is 1/1 billionth of a gram. A picogram is 1/1 trillionth of a gram. A femtogram is 1 whatever you would say. What comes after a trillion? Quadrillion, something like that, or 1,000 trillion. So, anyway, this is even smaller than that. So can you weigh this? No, our balance weighs here. Our balance is going to stop here. Well, the balance in that picture. You know, our Chem 4 balance only weighs here. It weighs to this. So this would be undetectable on our Chem 4 balance. If we try to put a helium atom there and weight it, forget it. It's going to weigh 0. You know, even though there could be some weight on there, it's going to be negligible. In Chem 1A, we do a little bit better. You know, these are cheap. Cheap being these balances are, I think, a couple of $100, $200. Our Chem 1A balances are like I think a couple of $1,000, and they weigh here 1/10 of a milligram. A tenth of a milligram is so sensitive that, you know, it depends on how sturdy the floor is. 1/10 of a milligram is if you're weighing something and somebody walks behind you, you know, it sets up a little air current. The air current causes the balance to fluctuate like this. 1/10 of a milligram means that if you touch an object and then weigh it, you're going to change the weight of that object because you're leaving your fingerprints on that object. And 1/10 of a milligram is enough to weigh fingerprints. So you got to watch out for leaving too many fingerprints on your object, because if you do that, the weight is going to go up and up and up. That's how sensitive 1/10 of a milligram is. There are other techniques. Well, how the heck did they weigh the helium atom then? There are other techniques that we use that don't weigh it using a mechanical balance like that. There are other techniques that use some physics to weigh it. And so you can weigh things that are extremely light like this using some physics, which we're going to talk about actually later. In a machine, an instrument called a mass spectrometer. So with a mass spectrometer, you can weigh these types of things. What you saw in the picture is something called a balance. So we'll look at balances. Balances are cheap. Mass spectrometers are quite a bit more expensive, like tens of thousands of dollars. All right. So it weighs that many. So, well, this is inconvenient. How many zeros is that? Well, that's 3, 6, 9, 12, 15, 18, 21, 22, 23 zeros, and then the 6. So that would be 20, 21, 24. This would be 24 spaces. So if we move the decimal place 24 spaces, 1, 2, 3, 4, 5, this would be 24. We can move it down to there. So if we move it to 24 places, it becomes 6.65 times 10 to the what? I moved it 24 places. So is this going to be positive 24 or negative 24? That'd be, yeah, negative 24, good. So that's going to be 6.65 times 10 to the negative 24 grams. That's how much a helium atom weighs. This is scientific notation, and this is what we're going to need to do. Okay, there are, okay, let's see. In 1 liter of helium, remember 1 liter of helium is very deceptive because how much helium is actually in that helium tank? You know, the 1 liter is fixed because this is usually a metal container. Is it a full tank or an empty tank? We don't know, because if you have 1 liter of liquid, it's fine. A 1 liter of liquid, you can easily tell. If you have 1 liter of water, yeah. But if that 1 liter water bottle is empty, then obviously you have 0 liters of water. Here you can't see it. You know, you can't look inside and see it. And so how much helium is actually in there? Well, how much helium is in there depends on the pressure. You know, usually you stick a pressure gauge and see what it is. Well, this is how much pressure. This is called 1 atmosphere pressure. 1 atmosphere pressure is just normal pressure. Normal pressure is the weight of the atmosphere, basically. You know, pressure is kind of the weight, or you feel pressure, or you feel the weight. When you feel the weight of the atmosphere, on a normal day, the atmosphere weighs about 14.7, 15 pounds per square inch. And so every square inch of you have 15 pounds of air pushing down on it. If you go inside a vacuum chamber, suck the air out. And actually, you can see what happens here. Actually, let me just show you quick, since we're talking about pressure and we haven't gotten to gases yet. I'm going to just show you this here, demo. Probably should have included in this slide here. So actually, let's look at, before I leave this, let me show you the images of this thing. This is the 5-story apartment building here, post explosion. This is the East Harlem gas explosion. This made pretty big news. But every year, like I said, natural gas, methane explosions kill people. So you ever seen this? We'll try this one. Let's see which one's shortest. 3 minutes, 2 minutes 50. We'll just do this one because it's a lot of marshmallows. I'm going to fast forward this because I probably don't want to watch the whole thing.
Build custom industrial machines.
All right, today I'm going to be putting marshmallows.
I'm going to just mute this too. So these are, right now, these are experiencing 15 pounds per square inch. Let me clear those drawings here. So we don't need to, just lower that. Okay, so 15 pounds per square inch, that's normal atmospheric pressure. And so this is a vacuum chamber. And so they're sucking out the air out of here. So what happens when you suck the air out of there? Well, okay, that wasn't as dramatic as I was hoping. I was hoping the marshmallows would fill the entire container. But you can see there's less and less pressure holding it. And then he's bleeding the air back in there. And so it's compressing the marshmallows again. So you can do that. And then you can add actually more air in here to force this to compress. And so it's a pressure chamber there, perhaps. Okay. So one way we can tell how much helium we have in there is by looking at the pressure of the helium inside the tank. And that'll tell us, if there's a lot of helium or not much helium. Well, it turns out there's going to be 15 pounds of helium per square inch in there, which is okay. But that's something called gauge pressure. And so if they're saying it's atmospheric, they're talking about something called gauge pressure. So there's actually 2 atmospheres, or about 30 pounds of helium in there per square inch, 30 PSI we call it. Where was I? Here. And so in 1 liter tank of helium at 0 degrees C, 0 degrees C, that's freezing point of water. So that's pretty cold, 1 atmosphere pressure. So that's actually 2 atmospheres. There's 1 atmosphere PSI G. There are 26,880,000, or maybe, I don't know what they're talking. Maybe that might be PSI A. That's not very clear from the picture. But anyway, there are a lot of helium atoms inside that 1 liter. There are 26, actually, what would we have here? So let's do this. This would be 1,000, which is a kilo. This would be mega, which would be 1,000,000. What comes after mega? What's bigger than mega? Megahertz goes to, somebody's got to know this. Not macro. Like say, oh, you know, my drive, my hard drive, you guys are probably too young for this, but you know, hard drives used to be like 40. I remember when getting a 40 megabyte hard drive. I was excited because I had a 20 megabyte hard drive. I had a 20 megabyte hard drive going up to 40 megabyte hard drive. I all of a sudden had twice as much disk space. Yeah, and so after mega comes giga. And then giga, we have tera, right? Giga to tera. So giga, so kilo would be 1,000, mega would be 1,000,000, giga would be a billion bits of data. And then terabyte would be trillion bits of data, 1 terabyte. What comes after tera? Does anybody know? Peta? Okay, I don't know because they haven't stocked those yet at the computer store. When they do, then I'll know, but I don't know. Actually, I don't know this, I don't know that, I don't know that. So we're just gonna use scientific notation. So how many, we moved it 3, 6, 9, 12, 15, 18, 21 places over, 22 places over. And so in terms of scientific notation, what would this be? So think about it. In terms of scientific notation, how would you write that? Well, there are 2 ways I'd write this. I'd either keep it, okay, the 2 ways I'd write it is I'd keep it between a number of 1 and 10. This is called the coefficient. So I'd go 2.688 times 10 to the, what was that? 3, 6, 9, 12, 15, 18, 21, 22 times 10 to the positive 22 or negative 22? Yeah, positive 22. You got it, Kazra. That would be it. Or I would call it 26.88 because I'd like to move in 3s. Since I like to move in 3s, I'd call it times 10 to the 21. Sometimes I'd write it like that, which is fine. If you'd like to move in 3s. But either way is good. And so that would be the number of helium atoms in 1 liter. Well, that's a big number. It's an enormous number. That's because helium atoms are so small and they don't weigh much. You know. How many grams of helium is that? Can somebody let me know how many grams of helium that is? You know, when we buy helium, we want to know how many grams of helium you're buying. So how many grams of helium are you buying? Calculator. Did I forget my calculator at home? I think I forgot my calculator at home. I'm just going to use my phone to calculate it. So for scientific notation, how do you do scientific notation? I needed to shoot. Today was not the day to forget my calculator. Gosh. Actually, do you guys, oh no, I didn't have it. I just had a lot of junk in here. So on my calculator, I do scientific notation by using this key here. It goes to show you I don't use my calculator enough. Here, right here at the bottom. I don't know, can you see that very well? Oh, what's going on with that background? Let's see. Let's see if I have a virtual background on. Yeah, I do. No wonder. Sorry. I use this key here. Your calculator might have a double E or an EXP key. Don't do scientific notation by hitting times and then punching in 10 and then raising it to some power. That's always going to be off. When you do scientific notation, always hit the scientific notation key, which is here on my calculator, or the EE key on TIs, I think, or the EXP keys. Yeah, except you can use the SD key, you know, scientific to decimal, but or fractions. Sometimes my calculator loves to do fractions because fractions you don't have to round. But the problem is will your calculator, can you input this many zeros in your calculator? Have you ever tried to input that many zeros? Try that. Try to input, let's see, how many zeros was this? 3, 6, actually I deleted it. 3, 6, 9, 12, 15, 18, 21, 24. Okay, so we need 23 zeros. So try this as an experiment here. What we're going to do is we're going to try to put in 23 zeros. What am I doing here? Let me get out of this mode. Okay, there I am. Okay, I'm going to try to put in 23 zeros, I said. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Oh, it worked. 665. And so I did it. I plugged it in decimal form. Let me hit equals and see. I converted it. I hit equals, but I miscounted because I'm getting 10 to the minus 25. I said it was supposed to be 10 to the minus 24, didn't I? And so I'm off. I'm going to multiply by 10. Now I got 10 to the minus 24. That's all right. And so that's how much one helium atom weighs. Then how many helium atoms did we have? Let me see if my calculator can handle that. Wow, this calculator is pretty impressive. It says 26,000, or not 26,000, 2688 plus 1 0, and then 3 more zeros, 1, 2, 3, and then 3 more zeros, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Oh, it actually worked. And so my calculator likes to give me things in fractions, because when you have fractions, you don't have to do any kind of rounding. In decimal form, oftentimes you have to round it. And so these are what we call exact numbers here. And then I'm going to do the S to D here, S to D, and I'll get it in decimal form. I don't know if this rounded it. It doesn't look like it did. 0.178752. And so that's, assuming I did it correctly, that's how many grams I have. And so this, I came out, and we double check our calculations. This came out to 0.178752 grams. Now there's some uncertainty here because this weight is what we call not so precise. It says 3 what we call sig figs, and this is more, a little bit more. This has 4 sig figs, so I'm going to round this to 3 sig figs. So this is going to be 0.179 grams, or I'll call it just 179 milligrams mg. That's not much helium. You know, 179 milligrams of helium. How much are you going to pay for that? Not that much. That's assuming I did it. I could be off, you know, and so since I'm off, I probably would rather just do this in scientific notation. In scientific notation, I do 6.65 times 10 to the, you know, I had that hit the scientific notation key times 10 to the 24, was it? Negative 24? Yeah, so negative 24 times, okay, and then this number was 2.688, 2.688 times 10 to the 22nd, like that, and then that equals, and so yeah, 0.178. So I had it right, and so that's only about 0.2 of a gram of helium, and so even though it's 1 liter, it's a 1 liter tank. There's not much helium in there at all. We're going to look at calculations like this. These calculations like this are very common in chemistry. You got 178 grams, not 0.178. Okay, well, let's do a little bit of, maybe we need another set of eyes. So right now you got 178, I got 0.178. I double checked my calculation. Did you double check your calculation, Kazra? Not yet. Okay, double check it. And if you get 178 again, let's get some more people to chime in and tell me what you got here. Anybody else? All I'm doing is multiplying these two numbers together. If I have this many helium atoms and each helium atom weighs this much, then if I have 2 helium atoms, I have to double this. If I have 3 helium atoms, I triple this. Well, if I have this many helium atoms, well, then I'm going to have to multiply these together because that's how many. This is called dimensional analysis. Anybody else do the calculation? You got 178 again. Okay, so this leaves the conclusion. Either you're right, I'm wrong, or I'm right, you're wrong, or neither of us are right. And so it'd be nice to have another person do the calculation. Can another person do the calculation? Okay, we're different by 3 decimal places, 3 orders of magnitude difference. And so what I'm going to do is I'm not going to punch in the zeros. I'm going to write this in scientific notation. So let's go ahead and write this. I erased it earlier, but this was 3, 6, 9, 12, 15, 18, 21, 23. Oh, that's where I made a mistake here. 3, 6, 9, 12, 15, 18, 21, 21, oh no, 24. 6.65 times 10 to the minus 24 grams of helium per atom of helium. This is the most common dimensional analysis type problem. So if I have 2.688 times 10 to the 22nd helium atoms, and each helium atom weighs 6.65 times 10 to the minus 24 grams of helium per helium atom, then we have the helium atoms cancel out here, and that should leave us with grams of helium. And so what does that come out to? Well, let's see what we're going to get. We can do a ballpark here. So let's call this 3 and 7. So 3 times 7 is going to, this is ballpark. This is what we call estimation. So 3 times 7 is going to be about 21. And then 10 to the 22 times 10 to the 24, we add these. So 10 to the 22 times 10 to the 24. So it's 22 minus 24, which is going to give me minus 2 grams of helium. And so this is a ballpark. And so the ballpark, this is going to be about, well, 10 to the minus 2, I want to convert that to decimal. So if I make the exponent, this is the exponent, if I make that bigger, I have to make the coefficient smaller. And so this means I move the decimal 2 to the left rather than 2 to the right. So make this bigger, make this smaller. And so it comes out to 0.2 grams of helium. This is my ballpark estimate. So I'm thinking it should be this, but let's punch out the numbers here. And so I'm going to punch out the numbers again, 2.688 times 10 to the 22nd times 6.65 times 10 to the minus 24. Okay, and again, this is the third time I'm doing it. The third time I'm doing it, I'm getting, this is my ballpark estimate. The third time I'm getting it is 0.178752. So, but this type of stuff happens, so we have to make sure we punch it in. Are you, Kazra, are you using the scientific notation key, or are you doing it? Okay, okay, you got it. All right, so you got it then. All right, so this is correct. And so only 180 milligrams or around 200 milligrams. It's not much healing at all there. Well, anyway, let's see what time it is. It's 2 now. Let's go ahead and take our break here, and we'll meet back in 15 minutes. So around 2:15, 2:16. 2:16 we'll meet again. Okay. Are there any questions before we break? Okay. I'm going to pause the recording. Okay, sorry. Okay, back here. And so for TI calculators, I think you'll have this key, EE. Let me make sure. TI-84. We had a question about that, so let's take a look quickly at the TI-84. Yeah, shoot. You're going to have to do second and then this, because do you see right here the EE? And so you'll have to do second and this. And so for you to punch in, let's say you need to punch in this number, 2.688 times 10 to the 22nd. Excuse me. You would have to key it like this, 2.688, and then second, this key, and then 22, and hit 22, and that should work. Okay. And so a little inconvenient because they should have had this as one key rather than a second function key in science. I don't know what the comma key is. Maybe it's more common. Not sure. Okay, any other questions on this before we move on? The technique that we used here, this is called dimensional analysis. Dimensional analysis. It's looking at the dimensions, the units here. That's what we're doing. Normally when we do like grams, we're using metric units. The SI units are the international system. SI stands for International System of Units. And we have something called the base units and derived units. And so the base units would be like length, You know what the SI unit for length is? International unit for length. Actually, I don't remember. It's either the kilometer or the meter. That would be a base. So length would be in meters. Weight or mass The SI unit, I think, is kilograms, but kilograms is usually too much for us. So typically we use grams instead of kilograms. Kilometers would be too much too for us. And so meters would be the most convenient, grams the most convenient here. What is a meter, you know, and how was that defined? And so a meter is just, we have a meter stick, right? And we use that, but originally I don't know who came up with a meter, you know. Let's say you didn't have a meter stick. How could you figure out how long a meter is? Would you need a meter stick in order to figure out how long a meter is? If everybody lost their meter sticks, could anybody figure out what a meter is? You know, those are important questions to answer. And if somebody makes a meter stick, you know, how do you know? Length from the nose to the tip of the finger, right? Yeah, that sounds right. But whose nose and whose tip of the finger? And so we need something that's very consistent, that's accessible to everyone, you know, to figure out exactly what a meter is. And so, do you know how they figured it out? How it's accessible to everyone? Well, it's not really so accessible to everyone. You know, we call that the definition. So what is the definition of a meter? The definition of meters can tell you if your meter stick is reading correctly. How do you know your meter stick is really reading correctly? How do you know somebody built it to the proper specs, right? And so we need to be able to test that meter stick against the standard. We call it, what is the standard for the meter? And so that standard is the definition or the standard of the meter. Definition, standard, meter. Let's see. And this is the way the meter is defined. This is a European spelling meter, by the way. So we spell it E-R. Why is it giving me R-E? This is accessible to everybody. The meter is defined as the length of the path traveled by light in a vacuum in, I need to get the whole thing, The meter is defined as the length of the path traveled by light in the vacuum in 299 million, sorry, one in 299, or basically 1 in about 300 millionth, 1/300 millionth of a second. That's it. The meter was originally defined in 1793 as 1/10 millionth of the distance from the equator to the North Pole. So if you take the distance between the equator and the North Pole and divide it into a million pieces, that would be a meter. So the Earth's circumference is approximately 40,000 kilometers. But, you know, this is a little less, you know, a little more difficult to measure, perhaps. This would be with modern day instruments. This is something that can be done, you know, measuring the path length of light here. And so this is the standard here, or the definition of the meter. Well, what's the definition of a gram? You know, how do you know your scale's reading correctly? How do you know if you have 1 gram or exactly 1 gram or close? And so how is that defined? The gram is defined by this. It's defined by the kilogram. And how's the kilogram defined? Well, the kilogram is defined as this chunk of metal. This is a chunk of platinum, I think it's platinum and palladium. PD, platinum is PT, palladium is PD. It's just this chunk of metal. And this chunk of metal is exactly 1 kilogram. So somebody has a chunk of metal that weighs exactly 1 kilogram. Why? Because they said it weighs exactly 1 kilogram. This is the definition of 1 kilogram, this chunk of metal here. Well, this chunk of metal is very valuable because this is exactly 1 kilogram, because somebody might try to copy this and be off a little bit, you know, a little high or a little low. And so it's got to be well protected. It is well protected. It's sealed in a different atmosphere. You know, they don't want any air in here like oxygen. Oxygen might attack the metals and oxidize it a little bit. So they want, although platinum and palladium are very resistant to oxidation. And so this is why you have these funny valves here. And the fact is a double bell jar. There are 2 bell jars here. There's 1 bell jar in here and another bell jar out here to help protect that. This is locked. This 1 kilogram standard is locked in some vault in France, the SI System Day International, whatever their headquarters. You know, that's where they lock that. U.S. has a headquarters like that. It's called the National Institute of Standards. They changed the name. It used to be NIST. Then they changed it, and then I think it went back to NIST. That's where we have the copy of this. You know, there are copies of this made, but there's only one original, and the copies are all going to be slightly off a little bit, you know, one way or the other, but negligibly slow. They're going to be very close to it. But this is not accessible to everybody. You know, this being locked away in the double bell jar like this is not accessible. And so the definition of the kilogram should be more accessible to everyday people. And so they're changing. Let's see what the new definition, they're changing the definition of the kilogram, the new definition of the kilogram. Okay, the new definition relates the kilogram to, amongst things, the equivalent mass of the energy of a photon given its frequency via the Planck constant. And so the old definition of the kilogram is this chunk of metal. Let's see. Which they call the prototype, the prototypical kilogram. The new definition is very sophisticated physics, but this can be repeated in some lab. And so everybody can know the exact, what exactly is a kilogram. Here's the physics, the equation of that. And so this is accessible to anybody who has this kind of sophisticated scientific equipment versus some kilogram locked in a vault, which is the international prototype of the kilogram. Okay. And so a little bit about that, but these are the base units here. And derived units would be like volume. For example, volume would be length cubed, you know, if the length times width times height, you know, length times width times height gives us the volume. So we have the base units of length, and then we can get the derived units. Or derived units might be like grams per cubic centimeter. This is the units for density. You know, that would be a derived unit. We have mass divided by volume. In fact, this is a cubic centimeter right here. This is 1 cc. That's 1 cubic centimeter, or 1 cc, or 1 milliliter. A cubic centimeter, excuse me, and a milliliter are the same thing. So that's 1 milliliter here. We like to use milliliters for volumes. And so cubic centimeters and milliliters are interchangeable. So this is reading in, you know, this would be 100 milliliters here, or 100 cubic centimeters. This is a very common instrument. This is what we call a triple beam balance here. Triple beam balances are cheap, you know, like rather than spending a couple of, well, actually now electronic balances are getting cheaper. So a triple beam balance might actually be more expensive than electronic balance. A couple hundred for the electronic balances in our lab, Chem 4 labs. This is an expensive piece of equipment here. What's this called? This is used to measure the volume of liquids. Anybody know what this thing's called? No? Okay, this thing is called a graduated cylinder. Graduated cylinder. And there's graduations here, so you can measure out different volumes all the way up to 100 milliliters. This is a beaker. A beaker is not really as accurate. You know, there are far fewer graduations, and it isn't properly calibrated, so beakers could be way off, you know. Graduated cylinder is much more precise and accurate way of measuring volumes. This thing is called a burette here. Burettes are very accurate and very precise ways of measuring volumes. Burettes have a lot of graduations here. This one doesn't have a lot of graduations, but this is very accurate way of measuring volumes as well. This thing here is called a volumetric flask, and it's only made for measuring one volume. And this one looks like 1,000 milliliter volumetric flask. I can barely make it out there, but this looks like a liter here. And then there's one line here that marks off 1 liter. So if you fill the liquid up to that one line, that's 1 liter or 1,000 milliliters. This one is also made for measuring only one volume, and this looks like a 20 milliliter pipette. And so this is called a volumetric pipette. This is a volumetric flask. This is a volumetric pipette. And you fill the liquid up to this one line here and then let it drain out. When we let it drain out, that's 20 milliliters. And the precision is quite good. So when we're looking at measuring these, I'll talk more about precision and accuracy, but this looks to be, I'm pretty sure that's a 20.00 milliliters here. This one looks to be 100.00 milliliters. This one is going to be 1,000.00 milliliters. And the burette, I don't know how high that burette goes, but it's gonna give us the nearest nearest hundredth of a milliliter precision. We call that. This is the 10th place, 100th. The next one, next level would be 1,000 milliliter precision. Here's our triple beam balance. We still have these in Chem 4. You just get the 2 weights equal. So you have a bunch of weights here and then you just slide it. A lot of people have these, you know, at their doctor's office or whatever. This is a 1/10 of a, actually this is a 100th of a gram balance. Oops. Back here. This is what we have in Chem 4. We have, this is 0.00, so it has a 1/10, a 100th of a gram precision, or 10 milligrams precision. This is what we have in Chem 1A. This is 0 point, and then 4 zeros. So if we go 3 zeros after the decimal being here. If we go 3, that would be a milligram balance. This is called a 1/10 of a milligram balance, right there. 1/10 of a milligram. And so these are all balances. Balances are used to determine mass in grams. Three different, these ones are, like I said, you know, a couple of $1,000 to $5,000. This is a couple $100. These, I don't know how much these cost. Sometimes it's a hassle saying, you know, 0.0001. 0.0001 grams is a 1/10 of a milligram. So oftentimes we use metric prefixes. So you should know these. You probably already know lots of these anyway. Those are so common. But let's take a look at some of these here. Which one should you know? Kilo for sure is big. You should know kilo. Let's go on the big side first. Kilo is 1,000. Mega. Mega has this symbol here. A mega is a million, or 10 to the 6th. Giga is a billion, or 10 to the 9th. Giga. Actually, you know what comes after giga is the tera, right? Tera has a capital T, and it's a trillion tera. And anyway, so that's on the high side. On the low side, hecto is not so common. Deca is not so common. So what are the common ones you should know? You should know these ones for sure. Know these. Probably already know these anyway. Deci is not so common. That's a tenth. You know, centi is common. You know, so we should know centi. Although these are factors of 3, 3, 6, 9, 12. Centi is the odd one because it's 2. But for sure we should know centi because centimeters is pretty common. Milli, micro, nano. So milli would be 1/1000th. I guess a small m. Micro has this. You know what this symbol is called? This symbol is the Greek letter mu. That's mu. That's 1/1,000,000th or 10 to the minus 6. Nano is n. That's 1/1,000,000,000th. Pico, p. That's 1/1,000,000,000,000th. 1/1,000,000,000,000th. And so this is 1/1,000,000,000th. This is 1/1,000,000,000,000th. Okay, so know these as well. Here. These ones you don't have to know. Although once in a while they'll pop up. Deci pops up in biology, you know, deciliter sometimes. But you don't really need it, you know, you can just talk in terms of liters or milliliters. Most people talk in terms of milliliters, it's easy. Or microliters or whatever you're dealing with. So when we take measurements, you know, we have to make sure we're recording the measurements properly. When we record the measurements properly, we have to account for uncertainty in the measurement. Oops, come on. Okay, this is a 1 meter stick, but you know, there's no markings on this 1 meter stick. Let's say all the markings rubbed off. Well, what would you call the length of this? Would you say, okay, if this is halfway here, I'd say that's maybe 0.6. I know what that is. I see the length of that. The length of this is going to be 0.635891236 meters long. Would you have much confidence in my measurement here? Would you say I'm right on? You know, I hit it. You know, I nailed this measurement. It's perfect. Would you say my measurement's perfect? No, I would have no. I'd have no confidence in this number at all. I'd look at this and I'd go, oh, it's more than halfway, but not quite 3/4, so maybe about 0.6 meters. Would I have confidence in that number? Yeah, I have confidence in that number, 0.6 meters. Because the way we take measurements is like this. It's going to be 0.6 meters, and then we have some uncertainty that comes with this. And so if it says 0.6 meters, I consider that about plus or minus half the smallest unit. This is the smallest unit is 1/10, so half of that's going to be 0.05, plus or minus 0.05 meters. And so what that means is that it could be anywhere, you know, based on this uncertainty, it can be anywhere from about 0.55 to about 0.64. Well, I'm going to keep it at 649 or almost, you know, almost there. We'll just say anywhere between 0.55 and 0.64 meters. This is the range of uncertainty, you know, that I see when I measure it like that. And so let's go with that. Well, in other words, this is in meters. If I do this in centimeters, this would be about 6 centimeters, 60 centimeters plus or minus about 5 centimeters. And so this goes anywhere from 55 to about 64 centimeters. You know, it's the range of uncertainty in that. Does that make sense? Okay, the next one we're going to look at is this. Now there's some markings here. So it's like it's between 60, halfway is 65. So it didn't quite make 65. So what would you guess this is? I'd probably guess this is closer to maybe 64 centimeters. Does it look like? And so here when I look at this measurement, it looks more like 64 centimeters roughly. Almost halfway. And so if I do 64 centimeters, then what I want to do is, what that means is it means it's 64 plus or minus half the smallest. Well, 1 unit is the smallest, so half of that would be 0.5 centimeters. And so the range that we're looking at in terms of this, the range of uncertainty, this is going to be anywhere between 63.5 to about 64.4. You know, I don't go all the way to 0.5, even though it should, because if I go to 0.5, it should round up to 65. It doesn't. And so this is the uncertainty. And so when I look at the uncertainty before, the uncertainty was about plus or minus 5 centimeters here, you know, in my measurement. Now this is what we call more precise, because the range of uncertainty is a lot more narrower. It's only between about 63.5 here and about 64.5 here. You know, that's that range of uncertainty. Whereas up here, I have a much larger range of uncertainty here. And so what we have is, we call this the uncertain digit. This is the guess digit. And so this is an uncertain digit, which is guessed. It's just estimated. And we're only allowed to estimate 1 digit. It would make no sense to estimate 2 digits. So when I'm looking at this, to estimate it at 0.64, I'm guessing 2 digits. I'm guessing 0.6 and I'm guessing 0.4. That's too many. I'm only allowed to guess 1. Here, I don't have to guess 60. It's definitely between 60 and 70. It's in the 60 range. So it's in the 60 range. So this is certain. I'm guessing the 4, you know? And so this is the guess digit. I'm only allowed 1 guessed or estimated digit when I make a measurement. This is just standard scientific practice here. And so this is my guess digit. That's the 4, which gives me a tighter range of uncertainty here. Now, when I look at here, I'm not guessing 4. I see it right here. This is the 64 line. And I see it's more than 64, but less than 65. And so here, 64, both of these are certain. For certain, it's above 64. For sure, see that. What's uncertain is how far beyond 64 it is. So is it all the way at 64.5? No. It looks like it's about 64.2, 64.3. So I'm going to guess 64.2 maybe here. So let's guess 64.2. And so here, the 0.2, this is the guess digit, or the estimated digit. I shouldn't call it a guess because we're just estimating that here. So if I have 64.2 centimeters, then what that means is I'll take half of the smallest increment is 1/10 of a centimeter. So half of that is 0.05. And so this is going to be 64.2 plus or minus 0.05 centimeters, which is going to narrow that range down. When we narrow that range down, the range is going to be between 63.7 up to 64.2, so 64 point, oh no, I screwed that up. Let me redo that. Okay. Are we doing this? It's going to be 64.1 and 64.15 to 64.24 centimeters. And so look at what's happening to the range. The range is being tightened up quite a lot, you know, range of uncertainty. This is the range of uncertainty here. Let's go to the final one here. When I look at this measurement here, it looks like it's just right before the line. You know, if I look at the shadow, I'm looking at the wood, not the shadow. If I look at the edge of the wood, it looks like it just doesn't quite make two. It looks like it's almost right on there. Might be right on there, but it looks like it just fell short, just a tiny bit. And so this one is looking like it's going to be a, for me, I read this and I look at that and I say that's going to be a 64.1. I don't have to guess, it's greater than 1. What I'm guessing is it's not quite all the way to 0.2, so I'm going to guess it's almost there. 64.19, maybe 64.18 centimeters. And so for sure I don't have to guess the 0.1 because I see the 0.1 line here. And it looks like it's almost to the 0.2 or the 20 line. And so when I look at the uncertainty there, we'd say it's going to be 64.19 plus half the smallest increment, and half the smallest would be 0.005 centimeters. And so that's going to give us this kind of range. It's going to range from 64.185 all the way to 64.194 centimeters. It's a very tight range. And so the range of uncertainty gets narrower and narrower, you know. And so, for example, if we look at the initial, we go back to this. If we look at the initial, the range of uncertainty was quite big, you know. Here. Range of uncertainty was quite big, and then we narrowed it down, you know. Then we're going to further narrow it down. This is blown up, and then further narrow it down, blown up. And so we call this precision. And so this is low precision, this meter stick. This bottom meter stick is high precision. High precision means a narrow range of uncertainty or an easier to reproduce result. You know, here you're going to get measurements that vary all over the place. Here we aren't, you know, it's very tightly controlled. So high precision means narrow range and more reproducible the result is. Low precision means a wide range of uncertainty. I'm talking about range of uncertainty here. And so this is the highest precision. Highest precision means we can, you know, remeasure this and get the same number consistently, whereas these are a little lower, so we'll be off a little bit more. Now, this is precision means this kind of this range, you know, or range of uncertainty or repeatability. Versus accuracy. Accuracy is a different story altogether. We can have the most precise looking thing, but it might not be accurate versus accuracy. Well, accuracy is who made this, you know? Maybe accuracy might be it's off, you know, at the end. We don't know. What if the end were off? You know, what if this person didn't line up the end? And so they accidentally lined it up like this. And so even though they might be taking very precise measurements here, they're going to be inaccurate because they're off. You know, we got to make sure that the end, they don't show the end. I don't know why they don't show the end, but the end has got to be lined up. Or maybe the meter stick warped a little bit or shrunk. If this meter stick shrunk, Is it reading accurately? You know, maybe it's old and starting to shrink the wood, or the wood warped a little bit, you know, and so that changes its accuracy. So accuracy is something different. Accuracy is, you know, how close the measured value is to the actual value. Accuracy deals with how close measured value is to actual value. And so what we need to do is we need to calibrate this. You know, when we have balances, we need to make sure, are your balances reading correctly? You know, are your balances reading correctly? And so we calibrate it. We calibrate it with using mass standards. Unfortunately, we can't get the one in France, but we could get other ones which are close. And so is this meter stick properly calibrated? Are we sure it's reading correctly? And that's accuracy. Precision is, yeah, we want higher precision. It's going to cost, this higher precision meter sticks can cost more than a lower precision one like this. But you're going to get more precise results, more consistent measurements, and more accuracy typically. They're usually built better. Okay, is that, yeah, range of uncertainty, or, yeah, this is and or. I should probably read and or, but it's or. This is different ways of thinking about precision. You know, high precision is a narrow range, and repeatable measurements. That is consistent measurements. Low precision is a wide range of uncertainty and difficult to repeat, to get consistent measurements, inconsistent measurements. So let's look at the dartboard analogy for this. If a person's throwing three darts, and so let's say dart 1 hits here, dart 2 hits here, dart 3 hits here. So they get 3 darts that are right next to each other, right on this spot here. Then this person is very precise, but they aren't very accurate because they missed the center, you know. If the person threw 3 darts and they hit the bullseye each time, then they're both very precise and very accurate because this person was aiming for the center but didn't hit it. Or another person might come and throw 3 darts. You know, one ends here, one ends off on the wall here, and one ends here, right on the bullseye. So 2 of the darts were pretty inaccurate. 1 dart was highly accurate. It hit the bullseye, but this isn't very good precision, you know. And so this is something we think about when we're doing measurements. All right, let's move on here. Okay, there we go. All right, now measuring volumes is tricky because we have something called a meniscus. This is the meniscus. When we look at the liquid, a liquid's not flat. Do you see the liquid's curved like this on the surface? The liquid's curved like this because water loves glass. Water wants to climb up the glass walls here. And that the water glass attraction is stronger than the water attraction. So this is why water is trying to pull itself up, but gravity is holding it down. So it can't climb up too far unless the tube's very narrow. If the tube's very narrow, then it can climb up pretty high. But anyway, so where do we measure? Well, where we measure is not in the middle. We measure at the bottom here. And so if I'm going to measure this volume here, I'm going to measure from the bottom of the meniscus here out. Oops, it's off a little bit. Come on. There you go. Try it one more time. See if I can draw a horizontal line. That's a horizontal line there, but it looks like it's tilted down. Maybe my drawing's off a little bit. Okay, so what we need to do is we need to get our eye level with the meniscus. So when we're reading this, this is a graduated cylinder, looks like. I need to make sure that I'm looking at it perpendicular to the meniscus. And that is, for example, if I'm looking at it, looking down at it, I'm going to take a measurement that's too high. If I'm looking at it looking up, I'm going to have a measurement that's too low. And so if I want just the right measurement, I got to make sure my eye is level with the meniscus here. And so I don't want this, and I don't want this. Get it at eye level. So usually, grad cylinders are light. You just lift it up to your eye, and you can just look at it, you know. Or you kneel down. A lot of people squat down so they can see it eye level. So let's measure this. Now, when we measure it, we're going 30 milliliters to 40 milliliters. So right in the center, this should be 35 milliliters. And so this should be the 34 milliliters. So we don't have to guess. It's between 34 and 35. So these first two digits are certain. It's 34 milliliters. So we're allowed one guess digit. And so where would you guess it lies in between 34 and 35? Yeah, I would say, I'd probably say the same thing, 34.5 milliliters. And so the 0.5 is our guess. We're guessing it's midway between there. And so we get 34.5 milliliters. Yeah. Okay, it's good, Ezra. Let's do this one. Why don't you take a moment and then tell me what you get for that measurement. Here, I'll take a moment. And let me pause this for a second. Be a little bit of time. You know what? Sorry, I missed it. It's the recording. I don't know where I stopped the recording. There's going to be a big gap in the recording. That's the problem, unfortunately. Sometimes I miss it. But just to do a quick review here, this one, we did the measurement. It was right on the line. This was 20.10 milliliters. Oh, I didn't want to do that. That was close to milliliters. What was this one again? This was 30.1234, 30.4. What was this one again? 30.45? Or did we do this one? I don't even remember. Well, this was 30.46 maybe? Or 45? 34.5? Oops, I did it wrong. You're right. That's not right. 34.5. 34.5 or 34.6, depending on where your eyeball lies. Okay, this was the guess digit. We were allowed one guess digit. Now let's move on. In fact, Didn't record the discussion for that. This was the burette. This was the volumetric pipette. And again, this was poorly measured. In case you're going off the recording, this was poorly done. Air pocket here, the meniscus not lined up there. Now this one here, let's take a look at this. So this is 1.0. Next one's 1.24682. So in other words, this goes 10, 12, 14, 16, 18, 20. And so when we look at this one, it looks like, okay, 12, 14, it's between 14 and 16. So where is it between 14 and 16? It looks like that's going to be 1.4. It doesn't look halfway. Halfway would be 1.4. It would be 1.5 would be halfway. It looks like it's slightly under 1.5. So 1.4. See how we're kind of guessing? The guessing range is a little bit big. So 1.45 sounds okay. No, that sounds okay. But hopefully you can avoid these, use a better grad cylinder. Here, what would you say? Which of these rulers has higher precision? The top ruler or the bottom ruler, or do they have the same precision? Yeah, B. B is higher precision. Well, higher precision means we can take more precise measurements. More precise measurements means a tighter range, less inaccuracy. So let me try to draw a vertical line here. Okay, what is this the same? And so in the top measurement, what would you get for the top measurement? .5, 3.4, 3.4, 3.4, 3.4, 3.4. Yeah, 3.4, I would agree. I don't think it's halfway. It's below halfway, looks like. Here, we don't have to guess. It's 3.1, 2, 3, 4. For sure, it's more than 3.4, and it's not quite to 3.5. So here, in this bottom one, what would you guess here? 3.41, 3.42, 3.41, 3.42, 3.41, 3.41. Got a lot of 3.41s. And for me, I would go closer to 3.242 on this one. The reason I'd go closer to 3.42 is because of this. I would draw in some imaginary lines in there. And so the imaginary lines would be my halfway line here, which I'm going to just kind of guesstimate here. Actually, that's off a little bit from halfway. Halfway should be a little bit farther over. And so that's my 3.4, what is that, 3.1, 3.2, 3.3. Sorry, it's 3.3. Oh, no, no wonder. My black line didn't scale. Sorry. I need to delete these. Or that. When I rescaled the drawing, my lines didn't scale with it. It was not a vector diagram. Okay, now, well, I guess it also depends on how you draw the line here. Let me just say, make sure that's a vertical line. Maybe that's not so vertical. Let me. Yeah, that is a vertical line. Well, that's a vertical line. Now it looks a little different. What would you say? It actually looks to me that this is more than halfway. If it's more than halfway, I'm thinking 3.46. Yeah, 3.46 for this one. That's good. Go ahead and type that in. These are part of your quiz. I'm just going to see if you guess 4 measurements. That'll be 4 points for the participation. And so we're guessing it's the 6, but the 4 we don't have to guess because I can see the 3.4 there. All right, let's move on here. Come on. It's not working. The mouse. Okay, maybe it was working. Okay, here you can see, you know, lower precision, like 28. Here they're guessing 8, you know. I probably, yeah, maybe 8, maybe 7. Maybe I would have guessed 7 on this. 7 or 8, 27 or 28 milliliters. Here, there's less guessing, you know, it's 28 for sure. You know, if I said 27, it's off. But they're guessing the 3/10, you know, 28.3. I might have called that a 2. You know, 3 would be 3, 4, 5. You know, so you imaginary 1, 2, 3, 4, 5. 5 should be halfway. So I would have probably called that a 2, 28.2. Here, there's less guessing here. Oh, well, this is a burette. Now we're upside down. We're flipped upside down here. And the burette starts at 0 at the top. So this is 28.123, and then almost halfway. To me, this looks like 28.34. They're getting 28.32, but I don't see that necessarily. I see it closer to half than closer to the other way. But you're going to do that. Whatever you do, you be consistent, you know, with your measurements. Just make sure. But the other thing you should do is compare your measurements with other students in class, you know, to see. Everybody should be getting similar measurements. But you should be consistent in how you divide the imaginary lines there, figuring this stuff out. Again, differences in precision here. You know, we're going to start looking at this now. One way, as in science, we have something called significant figures to do that. And the significant figures are going to give us an indication of the uncertainty and the precision. And so here, this measurement is to 2 significant figures. Significant figures is too long to write all the time, so I just call it SF. Sig figs, or sig figs for short. That's 2 sig figs precision. This is 3 sig figs of precision here. This is 4 sig figs precision. And so the more sig figs, the more precise. We're limited to the number of sig figs because we can only have 1 estimated digit, the 1 guess digit. We can't have more than 1 guess digit. And so here, this is our uncertain digit, 8. It's 8 because it's uncertain because it's guessed. 3 is uncertain because it's guessed. You know, I got 2. And here, this 2 is guessed. I didn't get 2. I got 4, 28.34 on mine. It's almost halfway. That's their guesses. That's 4 sig figs precision. Here, how many sig figs is this? Are you going to put a 0? Is the guess gone if you put a 0? No, the guess is like this. It's still, I'm guessing here. Do it like this. Okay, so this is just a hair above the line. But what if I'm right on the line? Sorry, this is not so straight, but what if I'm right on the line? So this is a hair above the line. So this is, what is it, 7, 8. This is 8 and maybe 8.1 or 8.2. So I'd call this 1.8, 1 or 2. Well, this is 5 here. So if that's 5, 1, 2, 3, I'd probably call it an 8.2, 1.82. Here, this is right on the line. So this is going to be 1.70. So we start off at 0 and then go 1, 2, 3, 4, 5. 5 should be halfway. So 0, 1, 2, 3, 4, 5. So it looks like I'm right on 0. Here, this is 0, 1, 2, 3, 4. Actually, you know what? It's close to 1. It looks like it's 181. You see, so the 0 is part of that guessing, you know, because I'm writing, you know, these imaginary lines here. Okay. And so the guess is not gone. I'm guessing it's 0 right at the start. Okay, the recording's still on. Just need to double check that. Let's see. I guess it's let's see. We stopped at break to 16, so it's time for our next break. Sorry, it's the past time for our next break. So I'm going to pause the recording here. Okay, we're going to resume here. I have a question. And that is, which of these two measurements is more precise? You know, this one up here or this one down here? Yeah, the top one's more precise. Which of these two measurements is more accurate? All right, accuracy, we can't tell, actually. The reason we can't tell is I don't know what they're trying to measure here. You know, we can't necessarily tell which one's more accurate because we don't know if these have been properly calibrated. And so if something is going to be accurate, we have to calibrate it against the standard. So if the balance is to be accurate, the balance has to be tested against the standard. So we can't go to France and get the kilogram, but we can get something comparable to it. It's called a kilogram or gram standard. And then we put that on the balance to make sure it's reading the correct number. And so, so for accuracy, we need to know the calibration history of these, you know, has it been calibrated? Do we know it's reading accurately or not? And so we can't really determine if either of these are accurate. Maybe neither of these are accurate. We don't know. It could also be inaccurate due to misalignment. Let's say we're supposed to measure the edge here. You know, this one's lining up with the edge, but this one's off. And so for sure, this one's going to be inaccurate. Well, this just so happens to be the less precise one, but let's say this one were off from the edge, you know? If this one were off from the edge, then yeah, that's a user error, you know, not an instrument error. And so accuracy deals with, is the user using the instrument properly? Has the instrument been calibrated properly? If we can answer yes and yes, then yeah, then it should be pretty accurate, you know, but we don't know. But for sure, this one's more precise, you know, than this one. All right, let's move on. Okay, what is this volume? Well, first off, this is a what we call a 10 milliliter blank. What is this called? Yeah, graduated cylinder. these little things are expensive. This is like $30, and so really pretty expensive. But what's the volume? So this will be, how many have we had so far? 2. So go ahead and type in your volume that you get for this one. That'll be worth a point. This will be 2C, I think. Are there any others? Okay, we'll stop here anyway. And talk. Yeah, 8.30, 8.31. 8.30 means it lines up right at the bottom. Now, what do you consider? Well, this is hard because they're not measuring this correctly. You know, really, they shouldn't have the line. They should have the line go all the way. So what they should do is they should rotate this. We want the line to go all the way across the meniscus. And so I don't think this is measured properly. Myself, that's my opinion. Because if you have a line like that, let's say this line here, what we need to do with this line is, let me see, do I have white? Yeah, I do. So they should have rotated this. Oops, that doesn't look good. Let me try that again. Let's narrow it up. In other words, I would have rotated this so the line goes all the way across, like that. So just rotate. I know the line's short, but we needed to go across the bottom, not halfway on the bottom. So when it goes across the bottom, do you see the black? It looks like the meniscus is a hair above because I see black, the black background peek through, and it goes all the way through. So I would go with 8.31 here. If I didn't see any black between the graduation here, the line, and the bottom meniscus, then I'd say 8.30. But for me, this is an 8.31. But anyway, both of those are very close. And whatever you are, be consistent. Like say, you know, where you measure it from the meniscus, be consistent. And again, the meniscus is this curved surface here. Okay. Well, how many significant figures is 8.31 milliliters? So we got, oops. There's, yeah, 3 digits, 1, 2, 3, 3 sig figs here. There are some numbers that have an infinite number of sig figs. Those are called exact numbers. There's no uncertainty. We have uncertainty here because of the 1. You know, we guessed the 1. Is that a 1 or is that a 0? We were guessing that. We didn't guess the 3. For sure it's a 3. You can see that there. But we were guessing, is it a 0 or a 1? So that's uncertainty. There are numbers that have no uncertainty. So let's take a look at some of these numbers that have no uncertainty here. Largely, these are by definition. You know, that's what if you see 3 lines here, it's usually by definition. And so 1 foot is defined as 12 inches. Is that, you know, is that uncertain? Is 12 uncertain here? You know, are we guessing? Maybe it's 11, maybe it's 13, but I'm going to guess it's 12. Is there, if it's 2 sig figs, that's the case, you know, we're kind of guessing it's 12, not 11 or 13. But in this case, we know that there is exactly, with 0 uncertainty, 12 inches in a foot. There's no uncertainty there. And so how do we handle that? In other words, do we do this? Do we call 1 foot, actually, let's go with a different color here. Do we call 1 foot, is that 1 sig fig? If it's 1 sig fig, then the range is 0.5 to 1.4 feet. That's the range of uncertainty there, because it's 1 plus or minus a half a foot. If it's 1 plus or minus half foot, then it's about 1.5 to about 1.5 feet of uncertainty. Would you say that's the uncertainty there with 1 sig fig? And the answer is no. No, it's exact. We call that an exact number. So it's exactly 1 foot. In exactly 1 foot, this is how we read it. In exactly 1 foot. In exactly 1 foot, how many inches are there? In exactly 1 foot, there are approximately 12 inches or exactly 12 inches? What would you say? Exactly, good. And so there are exactly 12 inches. When we're dealing with exact numbers, we say that there's no uncertainty. If there's no uncertainty, then they have infinite sig figs. And so really this is when we say 1 exact, it's an infinite number of zeros. It's infinite sig figs. When we say it's right on 12, it's 12 with an infinite number of zeros after that. And so this is infinite sig figs. And so 1 foot is 12 inches. But instead we just write it like this. The same goes. They're exactly 3 feet and exactly 1 yard. Exactly 1 mile is 5,200, exactly 5,280 feet. These are all definitions. For mass, 16 ounces in a pound, 32 fluid ounces in a quart, 16 ounces in a pint, 4 quarts in a gallon. These are the ones we learn growing up. You probably didn't learn these. This is exact. In exactly 1 inch, there's exactly 2.54 centimeters by definition. Somebody just decided to define it that way. This is also by definition. In exactly 1 pound, there's 453.59237 grams. That's a lot of sig figs. It's infinite sig figs there. And this is exact here. In exactly 1 gallon, there's 3.7854 liters. But these numbers are too hard to memorize, these ones. So what we do is we use inexact equivalencies. And so rather than memorizing that, what people will do is they'll just memorize something like this, which is perfectly fine. And so what I would do is I'd say 1 pound is equivalent to 453 point. I'm going to just go 1 more decimal. So what I'm going to do is I'm going to round that. So I'm going to call it 453.6 grams. And so now all of a sudden I went from exact, because there should be an infinite number of zeros here, an infinite number of zeros. I went from an exact number to not an exact number. And now this is 4 sig figs. So the way we'd read this is like this. in exactly 1 pound, in exactly 1 pound, there is approximately 453.6 grams. This is to 4 sig figs, 4 digits here. And so people usually memorize this. This is not exact. If you're going to memorize this, a lot of people don't bother memorizing this. The same thing here, you know, this is a lot of numbers to memorize. And so what people do for this one is they go 1 gallon is equal to 3.785 liters. This is also to 4 sig figs. So most people memorize these relationships to 4 sig figs, except for this one. This one, 3 sig figs is fine because the next digit's 0, 2.54. So in fact, it's all zeros after that. And so here, the way we'd read this is, how many sig figs here? Infinite. Here, 1 gallon. So in exactly 1 gallon, there's approximately 3.785 liters. And that's how we read it, to 4 sig figs. So exact numbers have infinite sig figs, Hazard? Yes. Yeah, exact numbers have infinite sig figs. That's correct. Okay, let's move on. If I can. Come on. Okay, there we go. Well, how do we deal with significant figures in calculation? So let's say I need to add up these masses. I have the beaker, and inside the beaker is chemicals A through D. And these are the amounts of each. And so I want to figure out what the total is. So when I add up the total, this is the number I get. But this number doesn't really accurately, well, I should be careful with the words. It doesn't actually represent the uncertainty in this. And so when I look at these, some of these are to a higher precision than others. For example, this one only goes to 1/10 of a gram. However, this one goes to the milligram, but this measurement goes to the nearest 1/10 of a milligram. This is the milligram to the milligram. So it looks like the highest precision mass measurement was to the 1/10 of a milligram here. It was the highest precision. The lowest precision one was only to the 1/10 of a gram. So a 1/10 of a gram, we could use a triple beam balance that gives us a 1/10 of a gram. But this one, we have to use a balance about, you know, $2,000 to $5,000 balance to get this kind of, this level. Well, here, that makes no sense. You use the $2,000 to $5,000 balance versus, you know, a garage sale balance that you could get like this. And that's going to impact the overall calculation. And so when we look at the guessed digit, we're only allowed 1 guessed digit here. And so this is showing the guessed digit. The 5 is guessed. The 0 is guessed. The 9 is guessed too. These are all the estimated digits here. And when I add them up, well, if the 10th has uncertainty, then the first uncertain digit is 8 here, this blue 8. And we're only allowed 1 uncertain digit. And so we have to eliminate these other 3. So we just drop them. And so we do something called rounding. So if we drop a 3 here, we leave the number the same. So we're going to drop the 3 there. We'll leave the 8 the same. If we drop a 5 or greater, then we have to round this up. And so we're only allowed 1 uncertain digit. Only 1 allowed. 1 allowed. Okay, we do that again here. Actually, this is the same thing. This is just showing it. Only 1. So this is for addition and subtraction. Addition and subtraction, the way we keep track of sig figs is the same. We look at how many decimal places of precision we have, and we stop it there, the fewest. And so we're only allowed one decimal place here. And that's what we only allow here. And so this is showing, you should always show the rounding step. This is the rounding step. So you should always show that. Don't just show the final answer here. For multiplication and division, it's a little bit different. For multiplication and division, we count the sig figs. And so this is 3 sig figs. We don't care about how many decimal places. This is 3 sig figs. This is 4 sig figs. So our final answer is only allowed 3 sig figs, regardless of the position here. And so, well, what about these zeros? Are these zeros significant? No, those zeros turn out to not to be significant, because if I could rewrite this in scientific notation, which would be 8.23 times 10 to the minus 2, or 82.3 times 10 to the minus 3. If I could rewrite it in scientific notation and those zeros disappear, then those zeros were not significant. So we don't count zeros preceding non-zeros, because those are just placeholders. We call these placeholders here. Placeholders are not significant. Now, if I rewrite this in scientific notation and the zeros remain, then those are not placeholders. You know? So for example, this is the 2 placeholders, and then 823, this is 3 sig figs. 3 sig figs. And so I go with the smallest number. I have 3 sig figs here, 4 sig figs. My final answer should have the smallest number, which is 3 sig figs, which this does. How many sig figs is this? 0.01350. How many sig figs is that number? Yeah, 4 is correct. Yeah. This 0 is important here. That's correct. How many sig figs is this? 1,350. Okay. For this one is a little bit ambiguous. This could be 3 or 4. 3 or 4. You know, it's a little bit ambiguous, because somebody might ask you, oh, there was an event yesterday. How many people were at the event? You say, oh, there were 500 people at the event. If there are 500 people at the event, are they talking about 500 plus or minus 1 person? Or are they talking about anywhere from 450 to 550 people? And so it's not absolutely clear when we have zeros after, you know, if they're significant or not. But if there's a decimal, yes, then it's significant. This is absolutely significant. This one is not, because it's a comma here. Well, we're going to get more practice with this anyway, so we don't have to cover all the rules right now. Okay, this is significant figures. Now we're going to, you know, so far we've measured length, and we've measured volume. Now we're going to look at measuring temperature. And it turns out we have 3 temperature scales that we can use. We have the Fahrenheit scale, the Celsius scale, and the Kelvin scale. And they're different, basically. The Fahrenheit and the Celsius are the 2 most common ones that we use. And so let's take a look at Fahrenheit and Celsius first. And we want to look at the relationship between Fahrenheit and Celsius. Do you know the relationship between Fahrenheit and Celsius? A lot of people do. Degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32 degrees. This is an algebraic equation relating Fahrenheit to Celsius. But where did this algebraic equation came from? This algebraic equation came from this. We're going to use our scientific method to determine it. Observation. So our observation is like this. When the temperature in degrees Celsius is reading 100 degrees, Celsius. What is the Fahrenheit temperature reading? It's reading 212 degrees Celsius. This happens to be exact. The boiling point, let's say, of water is exactly 100 degrees C under, well, I got to be careful, is under standard conditions, which is exactly 212 degrees Fahrenheit. There's no uncertainty there. Water boils at exactly 212 and exactly 100. It should, if the pressure is 1 atmosphere. And it freezes at 0 degrees C or 32 degrees Fahrenheit. And so this is the observation here. Then we look for a pattern. When we look for a pattern, oftentimes we graph things. And so let's put temperature in degrees Fahrenheit on the X. Let's start at 32 here. We're going to go 32 to 212 degrees here. And then we'll put temperature in degrees Celsius on the Y. So we'll start at 0 degrees here and go up to 100 degrees here. And so when I have 32 degrees Fahrenheit, I have 0 degrees Celsius. So I have a data point right here, the intercept here. And if I'm at 100 degrees Celsius, I'm at 212 degrees Fahrenheit. I have another data point here. It's this one here. Now, the relationship turns out to be linear. We could have non-linear relationships, but this one turns out to be a straight line relationship. And so this is what it's going to look like here. When I look at this pattern, if I see a straight line relationship like that, I can define this mathematically. I can define this mathematically by the equation of a straight line. What is the equation of a straight line? The equation of the straight line is y equals mx plus b. So what is y? Well, y is the temperature in degrees Fahrenheit. That's my y. And what is the slope? The slope is going to be delta y. So delta y is y final is 212. So this is going to be 212 minus y initial, which is 32. This is the units here of degrees Fahrenheit. Divided by my delta x. And so here's 0.1, here's 0.2. So it's 100 minus 0. So this is going to be 100 minus 0 degrees Celsius times x. X is the temperature in degrees Celsius plus the intercept. The y-intercept is 32 degrees. So that's plus 32 degrees Fahrenheit. And so I get this. The temperature in degrees Fahrenheit is equal to 212 minus 32 is 180. And then 100 minus 0 is 100. The units here are going to be degrees Fahrenheit over degrees Celsius times the temperature in degrees Celsius plus 32 degrees Fahrenheit. So 180 over 90 is 9 over 5. 9 times 20 is 180. 5 times 20 is 100. So 9/5. 9/5 is, or we could do it like this. We could do 1.8 over 1. Just move the decimal 2 over. So it's 1.8 over 1. So 9/5 degrees Fahrenheit over degrees Celsius times temperature in degrees Celsius plus 32 degrees Fahrenheit. And so this is our equation here. This equation we call a law, maybe. This is the law that governs the relationship between the Fahrenheit temperature and the Celsius temperature. And this equation is we'll call an empirical equation, an equation based on observation. This is the observation here. This is the observation here. And so this is the empirical equation that describes the relationship between Fahrenheit and Celsius. In other words, we can simplify it to degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32 degrees. That's it. And so we come up with a law, the law that governs the relationship between Fahrenheit and Celsius. That's it. What about Kelvin? Well, Kelvin's a little easier, you know. If we're at 0 degrees Celsius, we're at 273 Kelvin. If we're 100 degrees Celsius, we're at 373 Kelvin. And so the temperature in Kelvin is equal to the temperature in Celsius plus 273. Actually 273.15. That's what it is. And so that's the other relationship that we get here. So let's do some calculations here with this. Yes. Let me clear these. So we could do some temperature conversions. That's common. That's temperature conversions is algebra. And so, so for example, 37 degrees C is equivalent to 98.6 degrees Fahrenheit. That would be a temperature conversion like that. It's algebra. We could look at changes in temperature, delta T, changes in temperature. So this is absolute temperature here, or the temperature, the ambient temperature, let's say. 37 degrees C. And so that is the temperature. So the temperature in degrees C is equal to 37 degrees C. And therefore we can figure out the temperature in Fahrenheit. But what if we had a delta T? Let's say the delta T was 37 degrees C. If the delta T is 37 degrees C, is that equal to a delta T of 98.6 degrees Fahrenheit? Is this true or false? In other words, let's say the temperature dropped 37 degrees Celsius. If the temperature dropped 37 degrees Celsius, does that mean the temperature also dropped 98.6 degrees Fahrenheit? What would you say? True or false? Yeah. It turns out it's false. When we look at the delta T, okay, so we did that. We did delta Y. Remember that? Delta Y over delta X. Our delta Y was 212 degrees minus, this is degrees Fahrenheit, minus 32 degrees Fahrenheit. This is figuring out the slope from before. Divided by their delta X, which was 100 degrees Celsius minus 0 degrees Celsius, which gave us this, which gave us 1.8 degrees Fahrenheit for every 1 degree Celsius. This is the relationship for the change. So what that means is that a Celsius degree change, a 1 degree Celsius change is equivalent to a 1.8 degree Fahrenheit change. It's almost a 1 degree Celsius change is almost a 2 degree Fahrenheit change based on that. And so to answer this question, if the delta T is equal to 37 degrees Celsius, then this is the way I'd answer it. 37 degrees Celsius, and then we know that for every 1 degree Celsius change, we have a 1.8 degree Fahrenheit change. And so there's 1.8 degrees Fahrenheit change for every 1 degree Celsius change. And so that means it's 37 times 1.8. 37 times 1.8, better turn on my calculator. 37 times 1.8. Oh, come on. 37 times 1.8. It's 66. Actually, how many sig figs do I have here? Oh, it looks like I have just how many sig figs? And 37, how many sig figs is that? Well, that's 2 sig figs. So this is 2 sig figs. How many sig figs is 1.8? Okay, this is a trick question. It turns out that 1.8 is infinite sig figs. Now, how the heck did I get infinite? Because water boils exactly at 212 and freezes exactly at 32. So these are exact numbers here. And the same thing, this 1 is infinite because water boils at exactly 100 degrees C and freezes at exactly 0 degrees C by definition. These are by definition. And so this has infinite sig figs. So we're allowed 2 sig figs here. If we're allowed 2 sig figs, I usually carry extra. So this, if I carry extra in my calculator, it would look something like this. In degrees Fahrenheit, and then I'd round it. I'm only allowed 2 sig figs in my final answer, so I'd round this to 67 degrees Fahrenheit. So 37 degrees C temperature change results in a 67 degree Fahrenheit temperature change. Now, when we're talking about ambient temperature is offset. The zeros are offset. Do you see 0 here does not match 0 here. The 0 here is down here. If the zeros were matched, then it wouldn't be offset. And so the reason why I have to use this equation, the degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32, is this is offsetting the 0 here. The zeros are offset by 32 degrees here. And so I have to do that, make that adjustment here. And so this is why this is 98.6 rather than 67 or 66.6 here. Does that make sense? So when we're looking at the ambient temperature, we have to do the offset. When we're looking at a temperature change, we do not do the offset. We're just looking at, the size of the degree. Fortunately, Kelvin and Celsius have the same size increment, So 1 Kelvin is what we call the absolute temperature. The 0 again is offset. 0 Kelvin's way down here. 0 Kelvin has an important meaning. Does anybody know what 0 Kelvin means, or absolute 0? Have you heard the term absolute 0? It's actually defined. Absolute 0 has a definition. Absolute 0 is the coldest temperature possible. And what happens at absolute 0 is temperature is related to kinetic energy. So high temperature, high kinetic energy. As you get colder and colder, things slow down. Eventually you get so cold that they stop. When those vibrations, translations, and rotations stop, there's 0 kinetic energy. Interestingly, the electrons don't stop, but when the atoms stop vibrating, rotating, translating, molecules, atoms, whatever, then we are at 0 Kelvin. There's no motion. That's the coldest temperature. There's no such thing as negative motion, There's just motion or no motion. That's it. All right. So here, there are 3 types of problems that we're going to encounter with temperature. And so let me summarize the 3 types of problems that we encounter. Problem 1 is just a straight conversion. And so we just use equations. If you ever forget this equation, we could derive it, 9/5, how many sig figs in 9/5? Infinite sig figs. Because if you look at the origin of that, it's all from definitions. Infinite sig figs. This is exact, what we call exact. Degrees Celsius plus 32 degrees. How many sig figs in 32 degrees? This is also infinite, good. This is infinite sig figs because 32 degrees is from the definition. So both of these are exact. So your sig figs are going to be limited by the y or the x variable here. So types of calculations, types of calcs. The other type of calculation is delta t. For delta t, then we use a relationship that there's 1.8 degrees Fahrenheit change for every 1 degree Celsius change. This is it. Or there are 9 degrees Fahrenheit change for every 5 degrees Celsius change. Or et cetera, you know, whatever you want to use. These are exact. The last type of problem that we're going to do is this. This is what we call algebra. We have an algebraic equation. This algebraic equation just came from this is an empirical equation that we just derived from the graph here. Number 2 is an example of what we call dimensional analysis. Like that. The last type of temperature problem will be what we call multiple unknown, multiple equations. Let's say we have 2 unknowns. How many equations do we need to solve in order to determine 2 unknowns? Two, yeah, good. And so this is what we call system of equations. System of equations. System of equations. Let me give you an example of this. Is there a temperature at which degrees Fahrenheit is equal to degrees Celsius? Is there some kind of temperature, ambient temperature, in which the Fahrenheit is equal to the Celsius? Is that even possible? Let's say here it's 37 degrees Celsius is 98.6 degrees Fahrenheit, but is there a number here where the Fahrenheit temperature coincides with the Celsius temperature? No? Anybody else? Yes? Okay, we have a tie, or, you know, who's going to win, the no's or the yeses? So let's get one more person to answer. Is there Fahrenheit and the Celsius temperature that are equal? 2 no's, 2 yeses now? Well, we don't have to guess. Let's just solve it. How do you solve it? Well, we could do it. This is a multiple equation, multiple unknown equation. And so we have 2 unknowns. Okay, so degrees Fahrenheit is equal to degrees Celsius. Well, this is a problem because this is unknown and this is unknown. So unfortunately, we have 2 unknowns in one equation. So we need a second equation. And so what can I write as my second equation? Well, the second equation is degrees Fahrenheit. I know degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32 degrees, and then substitute. I'm going to substitute this in here for that, there. And so I'm going to 9/5 degrees Celsius plus 32 degrees is equal to degrees Celsius. Now I have 1 unknown in one equation. And so I should be able to solve this algebraically. And so what I'm going to do is I'm going to subtract 1 degree Celsius from both sides. So that would be 5/5. So I'm going to get 9/5 degrees Celsius minus 5/5 degrees Celsius. So I do that, and then what should I do with this? I'll just leave that on that side. Plus 32 degrees is equal to 0. Actually, what I'll do is I'll subtract 32 from both sides. And so what I'm going to get is 4/5 degrees Celsius is equal to minus 32 degrees. And so the degrees Celsius is equal to, well, 32 times 5. 32 times 5 divided by 4 is 40. So my calculation says that at minus 40 degrees C, that should equal minus 40 degrees Fahrenheit. So let's check this. I'm going to check it. So I'm just going to plug in 40 degrees C here. So let's go up here. I'm going to calculate degrees Fahrenheit is equal to 9/5 degrees C. So here's my check. I'll put minus 40 degrees C here. Actually, the units, the units are normally written here. So let's get rid of that. Plus 32 degrees. So what is 9 times 40 divided by 5? So 9 times 9 divided by 5 is minus 72. So this comes out to minus 72 degrees plus 32 degrees, which gives me minus 72 plus 32 is minus 40 degrees Fahrenheit. So this at minus 40 degrees Fahrenheit is the same thing as minus 40 degrees Celsius. And so this is an example of two unknowns and then multiple equations to solve it. We could do other things, things to see, So at minus 40, this is weird. At minus 40 Celsius is the exact same thing as minus 40 degrees Fahrenheit. But what about plus 40? Is plus 40 degrees Celsius the same thing as plus 40 degrees Fahrenheit? And the answer is no, they aren't. There's only one temperature there that the numbers coincide, and this is it. Let's try something else. Let's try another calculation here. Just one more example really quick. Is there, let's say, is there a Celsius temperature that's, actually, is there a, let's go with, is there a Fahrenheit temperature that's double the Celsius temperature? So let's say if the Celsius temperature were 10, the Fahrenheit temperature would be 20. Does such a temperature exist? Well, it doesn't look like it here, because if the Celsius is 37, if we doubled that, that would be 74, and that's wrong. So 37, that doesn't work, but maybe there is some other temperature here on the scale. So this is another example of two unknowns, unknown, unknown. So we need one more equation. The one more equation, well, that's easy. Degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32 degrees, and then we'll substitute that in here. And so we're going to get 9/5 degrees Celsius plus 32 degrees is equal to 2 times the degrees Celsius. So what I'm going to do is I'm going to do it this. I'm going to do 32 degrees, and then I'm going to rewrite 2 degrees Celsius as 10/5 degrees Celsius. And then I'm going to subtract 9/5 from that, minus 9/5 degrees Celsius. And so this gives me 1/5 degrees Celsius. And so it's going to be 32 times 5, 32 times 5, 160. So degrees Celsius is equal to 160 degrees. That means the Fahrenheit should be, degrees Fahrenheit should be double. So degrees Fahrenheit should be 320 degrees Fahrenheit. So at 320 degrees Fahrenheit, we should have 160 degrees Celsius. So let's see if that's correct. But let's just double check our calculations. So degrees Fahrenheit is equal to 9/5 degrees Celsius, which is going to be 160 here, plus 32. So 160 times 9 divided by 5, it gives me 288. So this is going to be 288. Plus 32. So 288 plus 32 be able to do that in my head. It's 90, oh, that's 320 degrees Fahrenheit. So it worked. There is. And so there actually is a temperature. So those are three methods that we use for temperature calculations that you'll encounter maybe in the chapter problems. Let's move on. Okay, that's temperature. We also measure density. And so what is density here? Let me write it up here. Density is the mass to volume ratio. M over V. Typical units are grams per milliliter. That's usually what we use here. And so we have the grams. We have 3 marbles here. The 3 marbles weigh 96.5 grams. So we just need the volume. This is measuring the volume of the marbles by water displacement. And so before we add any marbles, what's the volume here? Can you read the volume? It's hard to read. They need to rotate this, you know, because these lines need to extend. We've got to read it from over here, in other words. We can't read it from here because the bottom of the meniscus is not oriented towards the line here, but we'll just go ahead and do it anyway. So we got to figure out what are the graduations here. So this is 30, is that 31, 32, 33, 34, 35, 36, 37, 38, 40, 39, 40. No, that's not it. This has got to be 30, 32, 4, 6, 8, 40. So this is 40, 42, 46, 48, 2, 4, 6, 8, 50. Yeah. So these go by 2 milliliter increments. And so this is 60. This looks like about 61 milliliters, maybe. It's hard to see where the meniscus lines up. 61, maybe. I don't think it's 62. It's not right on the line there. And then this is going to, okay, 90, 92, 4, 6, 8. And so it looks like it's right below 100. So 90, 96, 98, 99 milliliters. This is not very precise. But anyway, it's all right. And so the volume is the difference. So it's going to be 38 milliliters. So I have 96.5 grams of marbles over a volume of 38 milliliters. I'm only allowed 2 sig figs here because of my earlier measure. 96.5 divided by 38. I'd like to read it more precisely, but the angle of the photos is bad. So this comes out to 2.5394.7. I have too many digits here. And so what I'm going to do is I'm just going to round this to 2 sig figs, 2.5 grams per milliliter. That's the, actually glass has a density around there. Glass is about 2.5 times heavier than water for a given volume. Aluminum's 2.7 times heavier. Did I miscalculate it? Well, anyway, it's not that precise, so I'm going to continue here. That's density. So let's look at some densities here on this sheet. And looking at some of these densities here, ice. Ice has a very open structure, and so ice is less dense than water, so ice floats on water. Look at this is interesting. What's more dense, mercury or copper? Do you guys remember the symbol for mercury? Yeah, mercury is more dense. It sinks to the bottom. What's the symbol for mercury? Hg, yeah. Hg is interesting because Hg is a liquid. Hg is the only liquid metal at room temperature. So it's got a pool of liquid mercury down at the bottom. If you try, the copper doesn't sink in mercury. The copper floats on mercury. So mercury is pretty dense. Mercury is like lead. It's that dense. Copper is around 9. Mercury is around 13, 14. Water is around 1. So water is the least dense of all these. So the copper is going to float. If you tried to swim in a pool of mercury, would you sink or would you float? In other words, could you drown in a pool of mercury? What do you think? Could you walk across an ocean of mercury? Yeah. Well, would you sink? No, you would not sink. Yeah, you would float on mercury. There's no way you could sink in mercury. You're not dense enough. In other words, you could walk across the surface of mercury and you wouldn't sink. You're certainly not as dense as copper. You're more like water, you know. Your bodies are made up mostly of water. And so you could either float or gently sink in water. Maybe you'll sink in water. Maybe you're a little more dense than water. You know. That's it. Depends on the water too. Yeah. Okay. Let's move on to the next one. Here are some densities. Helium is the least dense. We changed this. This is grams per cubic centimeter. A gram per cubic centimeter is equal to a gram per milliliter. For gases, this is inconvenient. And so for gases, we use a different unit. We use grams per liter. And so rather than taking a milliliter, which is a cubic centimeter, we use a liter. And so for helium, it's going to have a density of 0.17 grams per liter. For air, which is a mixture, it has a density of 1.2 grams per liter. And so if you had a liter of air, it's going to weigh 1.2 grams. If you had a liter of helium, it's going to weigh, you know, like 0.2 of a gram, something like that. Wood is less dense than water, so wood floats on water. Like pine is half the density of water. Oak is a little more, 0.8 of the density of water. Glass sinks. Glass is going to be 2.5. Aluminum is 2.7. Copper is 9. Mercury is 13.6. Lead is 11.4. Oh, I got these mixed up earlier, I think. And so mercury is 13. Lead is only 11. Lead is about half of the density of gold. I was wrong. I think I told you 13 or 14 earlier. It's 11. Gold is the most dense species on this. Iridium, osmium and iridium are a little bit more dense than gold, but not much. Yeah. And so these are the ranges of densities that we expect. You don't need to memorize. Of course, you don't need to memorize this. You just memorize. What we do in chemistry is we don't memorize individual observations usually. We memorize patterns and we memorize trends. Those are a little easier. Like wood. You know, wood is about half as dense, or a little more than half as dense as water. You know. Other species are about double the density. You know, then iron is heavy, copper is heavy, silver is heavy, lead, those are getting higher than gold. Yeah. So you should know the range of densities. You know, gold around 20, you know, and gases about 1,000 times less than water. Water is a good reference point here. This is not exact. This is 2 sig figs. Water's density changes a little bit with temperature. You should know this. Know the density of water to 2 sig figs. 2 sig figs. Okay. All right, now that's actually all chapter 3. And so we still have time. What we're going to do is I put some challenge problems here. These are going to be very big challenge problems for maybe Chem 4. But before we get to the challenge problems here, how do you learn problem solving? You know, and so what we're going to do is we're going to switch gears. You learn problem solving by seeing, you know, how people solve problems. You learn by example. And so I gave you 3 examples of using temperature calculation problem solving methodologies. And 1 was just a straight conversion. 2 was looking at temperature changes, and 3 was doing a system of equations. Are there others? You know, well, those are the 3 that I've encountered, you know, but what we want to do is we want to see, you know, how many different ways are there, and then we want to see, you know, what the variation is. You know, this is like, let's say you're studying a forest, a big forest, you know. What do you think is more effective? You need to learn the entire forest. Do you spend all your time just studying one tree in the forest? Oh, that's a very interesting tree. I'm going to spend all my free hours studying that one tree. But you end up needing to study the whole entire forest. Or do you try to study as many trees as possible, but, you know, and not spend too much time on one particular tree? And so when you're a beginner like this, my recommendation is to study as many different types of problem-solving methodologies as possible, you know. And I think it's a waste of time, at least initially, to spend too much time on one particular problem. And so I have a little bit different philosophy regarding homework than some of the other people, some of the other professors at El Camino. And my philosophy is this, you know, if it's starting to take too much time, then just look at the answer key. This answer key is at the end of the book. And so we just look at how they solve it. And so what I recommend is this. I recommend that you look at all the problems. You know, the ideal is you look at all the problems at the back of the book. If you look at all the problems, then you see all the ways that the book has solved problems. And then you can have those registered in your mind. Versus a select few. If you only look at a select few, it's like you have a whole forest of trees and you're only going to pick a select few to look at. But you have no idea what any of the other trees look like. And so how do you look at so many different trees? Well, you can't spend too much time, so you just look at the answer key, solutions guide. Some people say never open the solutions guide. In fact, most of the professors at El Camino say never open the solutions guide. That's cheating. You're cheating yourself. But I don't think so. I disagree. But anyway, let's take a break now, and then we're going to look at problem solving next. Okay. And so let's stop here. I guess I'm going to pause the recording. This is going to be one long recording. Maybe I'm going to have to stop the recording. I'm going to stop the recording here and break it up into 2 recordings. Otherwise, I don't know if I could load these on YouTube. Okay.